Hello, and welcome to FPGA Fridays. My name is Alex Ferencic. I am a postdoctoral researcher at UC San Diego. The research that I do is in data center networking and optical switching, and trying to use FPGAs to make everything work together. I'm also the maintainer of a project called Corundum, which is an open source FPGA-based NIC that's intended for data center networking research. Now today, I've got a couple of things planned. First, this stream is going to be a little bit of an experiment. I've learned over the last couple of streams that I did that I don't really code very well on the stream. So I'm going to try a hybrid approach this time, where the first part is pre-recorded, and then I'll come on live at the end to answer any questions. And this will allow me to remove any excessive time spent dealing with Vivado and things like that. So hopefully this will go smoothly. Okay, so as for the plan for today, I'm going to port the Corundum design to not one, not two, but 3 different FPGA boards. So these 2 boards were very kindly provided by the folks at Xilinx Research Labs to support the Corundum project. And this one was provided by a company called Silicom. This is one of their boards. So I'll give some more details about all of these guys. So you're probably thinking 3 boards, that's going to be just extremely tedious to make all of these work. Well, here's the thing. These 2 Alveo boards are almost exactly identical to a board that's already supported by Corundum. This is a VCU 1525. It's kind of the precursor or the prototype or proof of concept that predated the Alveo boards. And it's essentially exactly identical to the U200 production Alveo board. And then the U250 is the exact same thing, but with a bigger FPGA on it. So hopefully, the U200, supporting that is going to be as simple as changing the device settings and resynthesizing the design for this board, and changing a couple of device IDs and whatnot, and making everything as synchronized. So that shouldn't be too bad. For the U250, we may need to do a little bit of additional work because the FPGA is larger. It is pin compatible, and all of the I/O pin names and I/O bank numbers are the same, but the transceiver site naming is a little bit different, and we may need to tweak some of the floor planning, at least for the 100G design, in terms of which CMAX sites are used. So we'll take a look at that a little bit later. So that should be a little bit more interesting. And then the other thing is this card here from Silicom. This one is their Savona card, and I don't know if we can get a view on the name there. It's that focus doesn't seem to be cooperating today. There we go. Savona 03. There we go. So that's the code name for the board, which is a little bit less of a mouthful than. Let's see, what is the proper part number? It's FB2CG at KU15P. I don't know whose bright idea it was to put an @ sign in a part number, but there you go. That's a bit of a mouthful. Yeah, so this one is based on a KU15P FPGA, and it's a relatively economical board. So it should be a good option if you don't need a particularly large FPGA and you want to run Corundum. All right, so let's see here. I guess I'll start with porting to the Alveo boards. I guess we can take a closer look at these boards real quick, just to see if there's any particularly interesting features. These are all the actively cooled versions of these cards. So this is the original VCU 1525. And the LED configuration on the back is a little bit different. There's a couple of annoying features about this card. First of all, this screw gets in the way of installing it in most machines, so you might have to remove that screw. And then these LEDs also stick out quite a bit, so that can be kind of problematic. They solved that problem on these cards by recessing the screw and moving the LEDs as surface mount LEDs on the board. So, not really a big deal. There's not much to see on these cards unless you basically take them completely apart. Yeah, because everything is hidden underneath a gigantic aluminum block, and that's rather difficult to get off. Probably one of the most interesting features about these cards is that they provide 4 separate memory channels. So you might think, okay, with 4 memory modules on here, they probably give you, 2 memory channels, right? So these two will share a channel and these two will share one. But they actually went to the trouble of providing 4 independent memory channels. So as a result, the card gets like 600 to 700 gigabits per second of bandwidth into the DDR4 memory. And by default, these are all populated with 16 gigabyte memory modules. So that's 64 gigabytes on the card. That's you can do quite a lot of work with that. Now this is in contrast to something like the U280, which otherwise is a very similar card. But this one only has 2 DDR4 memory modules, and then it has the HBM. So 8 gigabytes of HBM plus 32 gigabytes of DDR4. So the nice thing about this is you get a huge amount of memory bandwidth, but the flip side is that's only 8 gigabytes. So if you need more memory, then maybe using one of these cards would be better, because you have, this one has 40 gigs total, these have 64, so. Oh, the other thing I'll mention as well is there's another important difference between the VCU 1525 and its direct descendants, the U200 and the U250, and the U280. This one was kind of more of a proof of concept. It's just, let's take a standard FPGA development board and put it in a PCI Express form factor, more or less. It doesn't give you really much in the way of peripherals. The relatively, shall we say, Spartan design, but it's designed to be used for basically whatever. The newer Alveo boards are specifically designed for compute offload applications. They're intended to be used with Xilinx's shell installed on the FPGA. And you're not supposed to work necessarily bare metal. I mean, you can, but they don't spend quite as much time in the design of the card and in the design of the software as they possibly could. So there are a few shortcomings with these cards. So there's a difference between the U280 and the U200 and the U250, and that's because these guys are basically direct descendants of this card. So anything you can do on this, you should be able to do on these. But the U280, let's see, the main difference here is that it hides away some of the transceiver control pins on the QSFP modules behind the baseboard, or sorry, the board management controller, the BMC. So in order to talk to the optical transceivers that might be installed in here, you actually have to talk to the BMC first, which then talks to the transceivers. On the other hand, on these guys, those control pins are connected directly to the FPGA, and the FPGA can also access the I2C bus that the modules are sitting on. So you have complete control over the modules here, and you have currently 0 control with the U280. That may change in a future revision of Avato, but we'll see. And for completeness, I'll also show the U50. This one is kind of a smaller version of the U280. It doesn't have the DRAM, but it does have 8 gigabytes of HBM, and it has a single QSFP. The other annoyance about this card is that it doesn't give you USB JTAG. It instead gives you this little 30-pin connector. And that one you connect via a ribbon cable to this little box that you have to buy separately. And this one has JTAG interface components for the FPGA and for the MSP430 board management controller. So I have not played around with this too much, aside from talking to the FPGA over JTAG, but there are a couple of interesting features to note on this board, namely in terms of the other JTAG headers that are present. There's an FPGA JTAG pinout here, or footprint, and that it would be interesting to see if you can use, say, a standard Xilinx platform cable to talk to this without using this little box. We'll see about that. It may be possible to make kind of an adapter cable. Then there's also the system controller JTAG header, and you can actually see that header on many of these other boards. So if I take, for example, the U200, there is a header right over here that says MSP. That's for the MSP 430 board management controller. So there's that one there, and there's another similar header over here that says PM bus. That's for talking to the power management components on the board. And this also has two PM bus headers. There's this one that says LTC PM bus, and then this one that says Intersil PM bus. So presumably those are for connecting to other pieces of external hardware. And then all the signals are routed through this guy over here. And then there's a couple of buttons that are not populated. There's SC reset, SC push button, and FPGA POR, which presumably is power on reset. So you can reset the FPGA or you can reset the system controller. So I'm definitely going to be taking a closer look at this to see at least if it's possible to use this card with a platform cable. Because these cards are pretty economical, but if you have to spend another couple $100 on getting a bunch of these, that's kind of a pain. Anyway, let's go ahead and get started with porting Corundum to the Alveo boards. Actually, I guess before I do that, we can take a little look at the board from Silicom. Let me get these out of the way real quick. Right, so this one, it's based on, like I said, a Kintex Ultrascale FPGA, the largest one, XCKU 15P. And this makes it relatively comparable to, for instance, the Alpha Data ADM PCIe 9v3. That one's based on the smallest Vertex Ultrascale FPGA, but since this one uses the Kintex Ultrascale, it's a little bit more economical. So this provides PCIe Gen 3 by 16. This is using the GTH transceivers on the FPGA, so those are capable of, I'm not sure what the number is off the top of my head. I don't know if it's 12 or 16 gigabits per second, but it's sufficient for PCIe Gen 3. And then it has a pair of QSFP28 modules that are hooked up to 8 of the GTY transceiver sites. And these are capable of 10G, 25G, 40G, or 100G Ethernet. I mean, for 40G, you need a soft MAC that's separately licensed. But for everything else, it's either supported in Corundum already, or you can get a free 100 gig, or it's either supported in Corundum already, or for 100 gig, there is the hard 100 gig MAC cores on the FPGA that you can generate free licenses for. Right, so what else do we have on the back? Well, we've got the pair of QSFP28s, then we have a whole bunch of LEDs here. So there's 8 LEDs that are associated with the modules, and these are, you can control these from the FPGA. Each one of these LEDs is actually a bicolor red-green LED, so you can turn on the red diode and the green diode separately. And then there's 4 LEDs down here that are connected to the BMC microcontroller, which is this part over here. See if we can get a better view of that. It says EFM32. It's a Gecko series part from, I think, Silicon Labs. And then over here we have the FTDI USB JTAG chip that's hooked up. Well, it's an FTDI USB interface chip, and it can be run in JTAG mode. And I think it's also connected to the BMC for debugging, and that's hooked up to the USB port here. Yeah, it's nice to see a card with a proper USB connector. There's so many dev boards out here that use these little micro USB connectors. For example, here's a Digilent Atlas board, and it has 2 of these micro USB connectors. It's not like they don't have space, right? The Ethernet connector on here is larger than the USB connector. But for whatever reason, they decided to use these horrible micro USB connectors. I say they're terrible because it's very easy to rip these connectors off the board and then destroy a very expensive FPGA board. There's a whole stack of like $400 Z boards in the lab that have had these connectors ripped off of them. So yeah, this is lame. This is nice. Now I will say, if you don't have space and you need to use a micro USB for space reasons, that's fine. It's also fine if, well, it's less bad at least if the connectors are protected by some sort of a bracket. So this is a ZC106, and in this case, the UART and JTAG connectors are protected by the bracket to some extent. And in this case, they're also using through-hole or partially through-hole connectors, so that's useful. Anyway, I think that's probably one of my favorite features about this board is a proper USB connector. And you could probably pick the whole board up by that connector and have no problems at all. Alright, so what else is interesting about this card? It's actively cooled, which is useful if you're running it in a desktop. That's actually one issue with some of the Alveo boards, is they make both an actively cooled version and a passively cooled version. And the passively cooled version will overheat very, very quickly inside of a desktop computer, because that type of computer generally doesn't provide sufficient airflow to cool the card. In a server, you've got like basically a jet engine in there that turns the whole thing into a wind tunnel, and these cards can actually keep cool effectively. So yeah, this one is nice from that standpoint, and it's actually rather quiet. It's much quieter than the alpha data boards. There's also a 12-volt input here. There's an adapter cable that it comes with that you can use to feed in 12 volts if you can't get enough power for your design through the edge connector. I can't remember what the limit is from the edge connector. It's covered in the documentation somewhere. I'll have to take a look. What else do we have on the back panel? There's a PPS in and out connector. That's an SMA connector. So you can't run a high-speed signal in here because it has relatively low-speed buffers. But, you know, if you need to bring something relatively low-speed in and out, this can be rather convenient. And then there's also a button down here. That's a recovery button for reloading the FPGA back to kind of a known good configuration. So from that point, you can then load a different configuration onto the internal flash. And what else? There's an expansion connector here that brings out, I think, 3 more of the GTY sites and 2 reference oscillators. And there's a little LED next to that, just a little red-green LED. And there's also a PPS in and out on the edge here. Let's see, I think the PPS out here is wired in parallel with the output buffer here, so you can't send different signals there, but the inputs are wired separately, so you can send a different input here as whatever you get from the input here. So it would be nice if this was wired separately, so you could actually send a different signal here, but whatever. That's not a major issue. But yeah, other than that, this is a pretty nice card. They also make, oh, actually another important point is that this card actually has 4 memory channels on it. So this card has a very similar amount of memory bandwidth to these Alveo boards. I think there are 4 channels that's 64 bits wide. I can't remember how much memory is on here. Obviously it's less memory, but it's a similar amount of bandwidth. This is in comparison to the alpha data board, which has only 2 channels of DDR4. So that one gives you about, I don't know, 250 to 300 gigabits per second or so. This one gives you more like 600 gigabits per second. So in this case, you might actually have enough memory bandwidth to, you know, fully buffer one of these QSFP interfaces, as opposed to on the alpha data board, you don't have enough for that. They also make a half-height version of this, which is very similar. I think it's passively cooled, not actively cooled, but it's a low-profile card, so it's much smaller, similar in size to the U50. So it's kind of about that size. That only has 2 memory channels, but it's also a bit cheaper. And I think you also lose the SMA connector, and the USB connector is on the inside and not on the outside. So that's also a nice card. It's let me put it this way. These things are about half the price of the alpha data boards, but they provide a similar amount of logic resources and similar capabilities in terms of interfacing. So you're going to build a cluster, and you don't need a gigantic FPGA. These boards are, I think, a really good option. Anyway, let's see if we can get Corundum running on these boards. All right, so let's go ahead and get started here. I have a clean copy of the repository. So what I'm going to do is go ahead and make a copy of the VCU 1525 subfolder so we can start working on code for the Alveo U200. So I'll copy the VCU 1525 directory to the AU200 directory. And once we get that more or less working, then I'll make another copy of the updated code for the U250. So the main files we need to edit are the top level XDC file. Let's see, FPGA core, and what was the other one? The top level make file. So I'm going to go ahead and delete all these output files. Okay. So I'm going to go ahead and pull up the XDC file that I put together for the Verilog Ethernet code here. So I will simply paste this in here. All right. So what do we need? We're not using any of those clocks. We have the LEDs. I don't think we use the reset button. Hang on, let me see here. What was the original thing? Yeah, okay, so no reset button, no UART, and we're using one reference clock, I2C and PCIe. Okay. Let's see, so one reference clock, yes, I2C. So the reset button goes away and the UART pins go away. Everything else is the same. Well, except these are a little bit different. So here's the part. As you can see, it's the XC U200. So they have an Alveo specific number for this part. All right, and then the PCI Express. Oops. I'm not sure why, but every time I specify both the N and the P pins, I seem to get warnings about something, so. Okay, there we go. That looks pretty good. All right, so now what I'm going to do is I'm going to take this part. All right, oh, I'm also going to edit the README, right? Need to change the board information here. So this is the Alveo U200. Okay, there we go. Let's see, so now FPGA core. Let's see, a couple things I need to do here. I need to change the board ID and the FPGA ID to match. I mean, it'll work if I don't, but oh, I also need to change the part here really quick in the make file. There we go. All right, so the board ID, that comes from the driver. So I'm going to go ahead and pull up the mqnix hardware.h file, which has the board ID for the U200. And it's 90C8 is the one that I selected. So we'll put that in here. Okay, and then I also need the JTAG ID. And the simplest way to get that is to go into an existing file. Let's see. I'm going to go into the code that I have synthesized for the Verilog design and extract. Let's see, is this going to show me something useful? Yes, it is. Excellent. So this is what the bit file looks like. If any of you have looked at a bit file, there's a header, and then there's a bunch of nothing, basically a bunch of Fs, and then there is a synchronization word and some other stuff. So what I've determined is that if you go down a little ways, you'll find the JTAG ID. And the way you'll recognize it is that it ends in 93, or ends at 093, because that's the Xilinx manufacturer ID. So the ID in this case appears to be 4B37093. 4B37093, and it's very similar to the code for the 1525, right? 4B37093. 4B37093. Okay, cool. So right now this isn't used for much, but eventually it's going to be used by the firmware update utility, so it knows what FPGA is on the other end. And the idea is it can do a simple sanity check and say, oh, okay, this bit file is for FPGA ID 4B37093, and the FPGA I'm talking to over PCI Express also reports that its ID is 4B37093. So it can compare that and give you a very basic sanity check. Unfortunately, this doesn't seem to work for encrypted bit streams, but it does work for normal ones. So hopefully that'll be sufficient. Okay. So let's see here. I think at this point, I'm going to go ahead and try running Vivado, and we'll see if this builds. All right. So that could be it in terms of the U200 10G design. So I'm going to let that run. And in the meantime, I'm going to go ahead and pull up the 100D design and make the same changes there. All right, so we've got, let's see, XDC, README, FPGA core, and the top level makefile. All right, cool. I'm going to do the same thing here, do a make clean real quick. Okay, so I'm all ready to run Vivado. I'll get that out of the way. All right, so let's see. Again, same thing. Oh wait, that's the old one. All right, I'm going to go ahead and swap out all these IDs. So this again is for, let's see here, the U200. So I'll copy that, and that will go here, right? The U200. Yes, and this is the Alveo U200. Okay. FPGA core, I need to change those IDs. I'll do that in a second. Makefile, that gets replaced. Oops, I copied that instead of pasting. I need to replace that one as well. All right. So copy that and paste that here. Okay, there we go. Now the FPGA core.v has to get these same two IDs. So I'm just going to go ahead and copy this whole block. Right, paste that in there. Looks good. Okay, now I need to move over the XDC file, so I'm going to go ahead and copy this and paste it here. And I think everything is the same, except we need to use both of the reference clocks. So I go ahead and bring this guy up there, and I think that's the only change that I need to make. Everything else should be the same. All right, so I'm going to go ahead and kick this off. Make, there we go. All right, so while these guys are running, I'm going to go ahead and get the U250 designs started. Okay. All right, so we're going to do the exact same thing here. For the U250, we've got both the 10G and the 100G designs, and this is the same idea here. In fact, well, it's not quite so simple as just doing a find and replace, because this changes to FIGD, and that U200, all of the U200s change to U250. Okay, so that's that, and this file here, this XDC, I need to copy that over again with the XDC for the U50. This is because the GTY sites are slightly different. I think all of them are different. Yeah, see, for the AU250, For the first QSFP, it's on pin N4 and IOB 231, but this is GTY4 channel X1Y44 and common X1Y11 versus this one is X1Y48 and X1Y12. So all of the site names are slightly different. All right, so I'm going to go ahead and copy this. That's the U250. And this one is going to be for the U250, so I'll paste that in here. And now we need to do the same modification. Let's see. Reset button goes away. UART goes away. And let's see. For 10G, this one is right, and then I need to do all the PCI Express stuff. So let's see. I'm going to go ahead and hit all of the XP, all of the P pins. Let's see. Delete that. Okay. I need the ref clock and reset, and there we go. Okay, so that looks good. And then I also need to edit. Well, now that I have this, I'm going to go ahead and make sure this is the same here. Okay, there we go. I'm also going to go into the make file and it gets updated here. Yes. Okay. Let's see. I need to update FPGA core as well with the IDs for this board. So let's see. If I go up to MQNIC hardware, this is 90FA. And let's see. Make sure this is the right board. Oh, that's the U200. These are getting interleaved now. FPGA core. Oops. Okay. There we go. FA. And then I need to get this. Let's see, from the Verilog Ethernet code, I can go ahead and pull the bit file here. And same thing, we get 4B57093. 4B, okay, that's right, 4B57093. Right, 4B57093, that looks good. All right, excellent. So we can save that. Now, I need to change the configuration for the two IP cores, right? Well, actually, no. This one should be correct because this doesn't specify any of the transceivers and the default sites should be correct. This one is wrong. I need to change the site names here. Fortunately, I already have the updated file here, so I'm just going to copy it over. So this one has 40 through 47 versus this is 44 through 51. So yeah, otherwise all the settings are exactly the same. All right, so that now means, I guess I need to open up another window here. All right, make file for the U250. Oops, Xilinx, Vivado settings. Now I can run. Did I clean this one? No, I didn't. Okay, now I can make, and this will run for the U250. And that'll take a few minutes. Okay. Now I will also do, finally, the 100G design for the U250. All right, so let me put this down at the end so I don't have any more interleaved files here. And let's see. Okay, so I'm going to need to edit those probably, and then the make file. All right, cool. So same idea. I'm going to go ahead and take this. Oh, wait, that's, yes, that is the U250. I will paste that over the 100G code. Same thing. I believe the only thing I need to do is turn on this reference clock. Sorry, that one. Oh. Hang on a second. Did I get the right reference clock turned on here? Yes, okay, good. Yeah, that is the U200 100G design. All right, cool. You want to be thinking ahead, just in case you make a mistake. It's much easier to restart Vivado than to wait for Vivado to complain about something. Yeah, okay, so readme, oh, I need to edit this one. These are, oh no, that's fine. Where was the U250? This one for the U250? Okay, I did edit that. All right, perfect. So let's see. This is for the U250, so I'll go ahead and copy that. and this goes into the README for the U250. I go ahead then and change the name. That's all U250. Okay, so I can save that, and then FPGA core, the U250, again, I need to copy over these IDs. Let's see. Here are the IDs, so I go ahead and replace that. Okay, there we go. That's for the U250, and then the makefile, I need to copy one more time from here, right? And that goes here. Okay, now the last thing I need to do is to update these couple of TCL files. Let's see, what's different here? Yeah, it's just the names. So the thing is, this one I'm not sure about, but this one needs to be adjusted. So this one, actually, I think, hang on a second, which way do I need to go? I need to go down by 4, right? Let me see. What are the site names here? I've got 40 through 47. Okay, so that means this one here, all of these need to go down by 4. Okay, cool. So I'm going to copy that. I'm going to paste this here because this is actually the correct values for this, except I don't know about the core select. And then all of this needs to go down by 4. So this becomes 40 through 43, and same thing here, 40, 41, 42, 43. And I think those site names are all correct. Let me make sure they're all X1. I think so. Yeah, X1, yes, okay, that looks good. All right. So what I'm going to do now is open up this project in Vivado and make sure that it's happy with those settings. Oops, OPT, Xilinx, Vivado settings. Let's clean it. So if I do make Vivado, this will open up, this will make the project file and then open up Vivado. Okay, so it seemed like it wasn't at least unhappy with those settings. Let's see here. This should be enough to go into the settings and make sure that all of the site names make sense. Let's see. CMAC US plus 0, CMAC US plus 1. Yeah, okay. Well, these do have different names. All right, so we'll take a look at this. All right, so we've got, let's see, here are the two CMAC instances. Now, let's see. This one is set to X0Y7, and this is set to X0Y8. All right, seems straightforward enough. So let's take a look at this then, and make sure this thing is happy with the selections. All right, so we go to the CMAC selection. We got CMAC E4 X0Y8, and the options are 3, 4, 5, 6, 7, and 8. All right, well, we'll try 8 and see what that looks like in the floor plan view after synthesis. Actually, how far do we need to go? Synthesis, I think, would be enough to show what's going on. All right, so the site names for the channels are 44 through 47. That seems fine. And as you can see, there's only 2 options in this list. So the thing with the Alveo boards is they disable all of the transceivers on the board that are not wired out to, physical interfaces. Interestingly enough, this does not show the transceiver sites that correspond to PCI Express. But it still shows you all of the CMAC instances, which is kind of silly because you can't hook them up to transceivers. Although on the flip side, I guess you can still use the hard RSFEC part of the core. So not completely useless. The funnier part is the PCIe IP sites, because it shows you all of the hard IP sites and all of the SLRs, except you can't hook any of them up to the transceivers except for the ones in SLR 0. All right. Well, at least I think it's SLR 0. On the U280, it's in SLR 0. I think on these cards, it might be SLR 1. Anyway, let's see, this looks pretty good. So I'm going to go ahead and run synthesis on here, and then we'll take a look at the synthesized design when that's done. All right, cool. That'll take a few minutes. In the meantime, we'll take a look at the Silicom card and see what we can do with that. Actually, you know what? Before I do that, let's take a look at the device driver and update things as necessary for the U200 and the U250. So most of the cards are all going to use kind of the same core data path logic. So there's really nothing there that changes. The main place that the board IDs are used is in this file, which is for the I2C interface. So what we're going to do here is very simple. We're going to go in and we're going to add the device IDs for the Alveo cards next to the VCU 1525 code, because I believe all of these cards have exactly the same configuration on the I2C bus. So this is relatively new code that made its way into the repository relatively recently. And what this does is it creates I2C adapters for all of the I2C pin pairs on the FPGA. And then it goes through and it creates I2C MUX instances for I2C multiplexers that are on the board. Not all of the FPGA boards supported by Corundum have these multiplexers. Most of the Xilinx boards tend to have one I2C interface for everything and then a bunch of multiplexers. Some of the other boards tend to either have separate I2C interfaces, so there might be one I2C interface just for the MAC address EEPROM, and then one I2C interface for each optical module, or you might have one I2C interface for both optical modules that's kind of shared in some way. Right, so for this, the main thing I need to do is add the board IDs. So this is going to be, what were those called again? MQNIC HW. Okay, so AU200 and AU250. So I'll do AU200 and AU250. And I think that's the only thing I need to do to make this work. Right, so these only have a single I2C interface on them. I actually don't know how to access the EEPROM, or sorry, the MAC addresses on these things. At least on the 1525, there is an EEPROM on the board that's accessible by the FPGA, but it doesn't appear to have a MAC address programmed into it. Although I should probably double check and make sure that's the case. I thought the last time I checked it didn't, but I'll double check just to make sure. Yeah. On the U280 and U50, you have to read the MAC address out of the BMC microcontroller. So I'm going to look into that at some point, but as of right now, that's not implemented. So on those cards, they don't come up with the pre-programmed MAC addresses. Okay, so I think that's all that needs to be done here. For the Silicom card, it's going to be a slightly different story. All right, well, let's go ahead and take a look at that card then. I'll go ahead and pack these guys up real quick. So for that card, I'm going to make a copy of the alpha data design because that's the one that's most similar. Let me get rid of that. Let's check on Vivado here. Oh, it's let's see. It's still doing the out of context synthesis. It takes a while to synthesize the PCI Express IP core. All right, let's see here. So I'm going to go ahead and open a terminal. Oh, wrong folder. Well, doesn't make that much difference, I suppose. All right. I'm going to copy this guy to, what was it, FB2CG. Let me make sure that's correct. I believe I have an XDC file waiting for it. Yep, okay, there we go. FB2CG at KU15P. All right, very cool. All right, so that went ahead and created that folder, FB2CG. All right, so I'm going to take these one at a time. I'll start with the 10G design and we'll go from there. I'm not sure I'll get to all of them today, but at least if we can get the 10G design working, then that's a start. All right, so I'm also going to open up the README for this here. All right, so let's see. This is for the Silicom card here. And that's XDKU15P for the FPGA. All right. And then the XDC file, I will copy that from here. I'm not going to waste a lot of time creating this. All right, so let's see here. This has both ref clocks wired up, right? Power good pins, LEDs. We'll leave out the GPIO and the BMC interface for now. And this uses an init clock on the board that's running it at 100 megahertz. And this one is coming in on a non-clock capable IO pin, or there's something funky about the pin that this is connected to, so it needs some additional help. Okay. And then I need to bring up, I don't need the expansion connector, and then I need PCI Express. All right, so I'm going to go through all of these. All right, and then again, I need the reference clock and reset line. All right. Okay. It looks like Vivado is now synthesizing the AU250 design, so I'll get back to that. Well, as soon as that's done, which could be a few minutes. Okay, so that looks good. Now we need to start taking a look at the core code. So in this case, we need FPGA and FPGA core. And I'm also going to need to modify the test bench and the IP cores as well. So I think these, this one probably doesn't need to be modified. PCIe 4 Ultrascale Plus. Yeah, that actually should be fine. This one I will copy over from the Ethernet design. Same thing. This should have all the site names. It's 12, 13, 14, 15. Skip a quad, 20, 21, 22, 23. Yeah, so this actually starts out 12, 13, 14, 15. But then it doesn't skip a quad. I don't know why they skip a quad on that... on the Silicom card, but they do, so whatever. And then we're using clock 0 on both of these. Okay, so that's looking pretty good for now. Okay, so that's that. Now we can go into FPGA.v. So I'm comparing this to the Verilog Ethernet code. And most of the stuff is going to be more or less the same. Well, hang on a second. I think there's a couple of things I need to bring in here. Yeah, I need to bring in the I2C pins for the modules. So with this one, it doesn't have an onboard EEPROM for the MAC addresses. The MAC addresses have to be read out using the BMC. You use the BMC to read a flash page, basically, that has the MAC addresses in it. So I'll deal with that a little bit later. But the nice thing is that each QSFP28 has its own I2C interface. So that's going to be useful. On the Alpha Data board, there is one I2C interface that's shared between the two optical modules. And then you have to use the mod cell pins to select which module you want to talk to. So having two separate interfaces is rather nice. Okay, so let's see. I need all of this stuff here. Init clock, LEDs, and the PG pins. And this goes into FPGA.v. Let's see, so that's going to replace this stuff. And there's also PCI Express. Let's get all this stuff lined up. Okay. Now, how is the naming? This looks very similar. Okay, so the pins are a little bit different. So MGT ref clock PNN, that looks fine. Okay, so these are a little different. All right. And then I need to add the I2C pins. Is that just SDA and SCL? Possibly. Or is it I2C? It is I2C SCL and I2C SDA. Okay, so the I2C pins are in and out. Okay. And then this is I2C, SCL, and SDA, right? Which way is that going to go? Previously it was SCL and SDA, so I'll keep it the same. All right, cool. So I will go ahead and copy this and put the, well, actually, I'm going to copy all of that and put it down here. So that's all on the other channel. And there is no QSPI, there is no EEPROM, and there are no shared pins. All right, there we go. That's pretty good progress. All right, so now FPGA core, how much of this gets passed through to FPGA core? Let's see, I think what we're gonna pass through, basically pass through everything. Except the let's see, the I2C stuff gets passed through a little bit differently. All right, so I'm gonna go ahead, I'm gonna copy this over and rename it. Well, I don't need to rename this, do I? I need to update the I2C lines. So 2 are going to become 6. I need to get I, O, and T, and I need input and output. Okay, so that's I, O, output, and T. That went smoother than expected. Okay. And now all of this gets replaced. Oops. There we go. And the QSPI also goes away. Yeah, I'll bring that back later. Okay, there we go. So that's the stuff for QSFP0 and the stuff for QSFP1. All of the PCI Express stuff. Oh, and then the LEDs need to be updated as well. And I'm going to copy those from FPGA core. There we go, GPIO. Here are the LEDs. All right, let's go ahead and tab that all the way in. All right, there we go. And all of those are fine. So let's see, the next thing that we need to do is update the board IDs. All right, so the FPGA ID, I can go ahead and extract that same way as the other one from the bit file. There we go, fpga.bit. And this one is offset differently than what I was expecting. 04A56093 with an additional 3. Really? 4A56093. 4A56. 4A56093. 4A56093. That's the only 93 that's in here, right? Well, maybe I'm just confused. Let me take a look at one of the other ones, just for comparison. I was looking at the U250. Oh, so never mind, that's fine. It's just offset by 1 byte. Okay, this one, yeah, that's fine. All right, I thought it was offset by 4 bits instead of a byte. Okay, so that looks fine. Now I need to pick a board ID for this guy. Let's see. I need to see what that board is reporting over LSPCI, and I will just use that. Okay. Bravado just completed for the U250, and it has 2 critical warnings. Go figure. What is that all about? Ah, I need to comment out the ref clock timing constraints, actually. Where was that? FPGA.xdc. Yeah, so these become redundant. I forgot about that. The CMAC cores contain the timing constraints. The GTY or GTWizard instances do not. That's okay. The main thing I want to look at here is what the synthesized design looks like in terms of the floor planning. The main thing is I want to make sure we're picking the most optimal sites for the CMAC hard cores in relation to the transceivers. So let's take a look at what this looks like in terms of the floor plan. As soon as Vivado finishes, I don't know what it's doing. Vivadoing, how about that? I don't know why it takes like 5 minutes to open up the design. And this is not even the implemented design, right? This hasn't even placed anything onto the chip. Well, I guess it's placed a couple of things. The PCI Express hard IP cores and possibly also the CMAC cores will be placed somewhere and fixed in position. Everything else, though, it hasn't run implementation yet, so it hasn't been placed yet. All right, there we go. Yeah, so here I think is the PCI Express IP core. Yep, PCIe 4.0 instance. Yep, that's fine. PCIe 4 to E4. Yeah, that is that. All right. And how many SLRs does this chip have? Does this just Oh yeah, this has a whole extra SLR. This has a whole SLR3. All right, so that's the difference between the two. On the U250, you get a complete extra SLR. Okay, so these are the CMAC sites, right, that were selected. And now the question is, what happened to... Oh, I think they're on the wrong side of the chip, aren't they? Ah, there we go. All right, here we go. So this is, yeah, these are the two sites here, one site and the other site. Okay, so this is associated with, okay, here's what I'm going to do actually. I'm going to zoom out here. I'm going to highlight all of the leaf nodes on this guy. Highlight leaf nodes and make it pink. We're going to make sure we're not crisscrossing. Okay, it highlighted that, but what about this? That's annoying. That's number one. That's CMAC 1. CMAC US plus 1 GT. Oh! Oops. I didn't highlight what I wanted to highlight. I highlighted just the GT cores. Let me unhighlight that, and let me go up a couple of levels. There we go. Let me highlight that. Highlight leaf cells. Same vibrant color. All right, there we go. So now you can see that this CMAC is hooked up to this set of transceivers, and they line up nicely. And then if I do that for the other CMAC instance, I think we'll get the same result. If I highlight this one, how about some other equally bright color? Yeah, there we go. Right, so these line up. This should be good. All right, excellent. So I think I can now run the full thing, and we'll see what happens. Okay. Did I have a placement constraint on these? One moment. I don't think I did. Oh, well, I don't have one on this one. I may have had one on the 1525, maybe. I'm not sure about that. Anyway, if we need one, we can add one. It's sometimes Vivado doesn't do a very good job with SLR crossings, so I've had to add a P block on one of the SLRs and force it to put a lot of the PCI Express logic in that P block. Otherwise, it might put SLR crossings in really bad spots and totally screw up the timing. Anyway, let's go ahead and run the implementation here, and we'll see what it looks like. All right. Excellent. So that is now going to run. Okay, so where were we here? I need to boot up my development machine and take a look at LSPCI. One moment. Whenever you turn that thing on, the U280 fan spins up to like 5,000 RPM. Sounds like a jet taking off, and then, 10 seconds later it spools back down again. So there seems to be a bug in the BMC on the 1525 board that I have, because half the time when you power it on, the fan doesn't spin down, it just spins running. It just continues running at, like 100% thrust. It's rather annoying because it's very loud when it's at 100%. Anyway, all right, so let's see. That's booting up. Then I can figure out what the board ID is. I also need to add a board ID to the driver, right? Let's see, MQNIC hardware. It's going to go in here somewhere. I'll figure that out in a minute. Let's see, define new board ID, and this is the FB2 CGKU15P, right? Yeah, I think so. And then I'll figure this out in a minute. Okay. And then the other thing we need to do with this is go in and update some of the other code as well to use this ID. Specifically, I'm going to need to make a new entry in here somewhere. Yeah. Okay, so this has so these cards have an EEPROMs on there. So I'm going to have to make a copy of one of these. I guess it doesn't make too much difference which one. I'll go ahead and do that real quick. This is pretty straightforward. Okay, so this is MQNIC board ID. Let's see, this was FB2 CGKU15P. Okay. And there are two I2C interfaces. Let's see, and this is QSFP0 and QSFP1. I will need to double check. Oops, that should be QSFP1. This is I2C0 and this is I2C1. Okay, very straightforward. I do not need a MUX. I do need that. That looks good. I2C adapter. Okay, so this is QSFP0, right? And then I need another I2C adapter for the other one, right? This is going to be I2C1. And then the other, oh, wait a second. I screwed that up, didn't I? I want to use this guy for QSFP0. And it's not that. This is going to be directly on the adapter. Okay. Then I have another one of these for QSFP1. That goes here. And then I think, and then I need to set I2C client count to 2 because I have 2 modules. And then I think that's all I need to do. Okay, let me just remove these reference indicators here until we figure out what the actual names are on the board. But that's okay. All right, I can do that later. So this looks pretty good. So this is the kind of stuff that you need to add to the driver to make everything work. This one is, this sets up the I2C adapters for the 2 I2C channels that the board is exporting. So some of these other boards, like I said, export 2 interfaces, like the X10 and the X25 and the Alpha Data ADM PCIe 9v3. These have a separate I2C interface for the EEPROM. Now I actually don't have the module side done yet because I need to that code is a little bit more complicated. I have run into a couple of minor issues with that I have yet to fully figure out. But yeah, that's on my to-do list. And once that's done, then you'll be able to access the I2C bus on those boards, again, through the driver. So the cool thing about this is this will allow you to, well, it does two things. One, it allows you to read the I2C information, or read the I2C EEPROM in the module from user space using ethtool. And that one will provide information, if you have an optical module in there, about what the bias currents are for the lasers, what the wavelength is, if it's a WDM module, and it will also tell you what the receive power levels are, or a rough measurement of those. I don't know how accurate those are, but it does give you a number, and that can be very useful for debugging. But it also lets you change settings on the modules, and that's very important if you say want to take a 100 gig module or a 25 gig module and run it at 40 gig or 10 gig. In a lot of cases, the modules have clock data recovery circuitry in them, CDR circuitry, and that needs to be disabled in order to use it at well, a non-standard line rate. Some of them are smart enough to figure it out, but for a lot of them, you need to turn the CDR off if you want to use the CDR, or if you want to use the module at 10G instead of 25G or 100G. So that's done over the I2C interface. Okay, let's see. So that's looking pretty good. Now, what's the next thing we need to do? So in FPGA.v, I need to take the init clock and feed that into the PLL. And I have some code for this in the Ethernet design, so I'm going to go ahead and transfer that over. Wait a second, that's the wrong board. Okay, I need this one, FPGA.v here. Okay, so I need to do two things here. I need to, let's see, instead of using an iBuffG DS, I need to use a BuffG, and I need the init clock BuffG. Yeah, so that replaces that. Oh, and this one actually should be moved here. Okay. All right. And I'm also going to copy over the actual PLL so I get all of the PLL settings correct. So on the alpha data board, it brings in 300 megahertz. So I guess we can just take a look at that real quick. 300 megahertz in, 125 megahertz out is what we want. So we divide by 3 and then multiply by 10 to get a 1 gigahertz VCO. And then you divide that by 8 to get 125 megahertz. So there's your divide value, there's your multiply value, there's your input divide value, input clock period. And the input clock is here, and the output clock is here. Pretty straightforward. Okay. In this case, we bring in 100 megahertz, we output 125, so it's exactly the same thing, except we divide by 1 instead of 3. Piece of cake. Okay. Let's see. So the reset, in this case, I also need to consider the PG connections from the BMC. And these will indicate when the regulators are all doing their thing and are outputting the right voltages. And it also includes the PLL loss of lock signal from the Silicon Labs PLL chip on the board. So when that's locked, then one pin or the other, I can't remember which one it is, includes that state, goes high, indicating that everything is good to go. And until then, all of the reference clocks for the transceivers are not running. So you don't want to bring the transceivers out of reset. Okay, let's see. So I think that takes care of most of the clocking stuff, because we have init clock coming in through a BuffG, output, bringing that into the PLL. And we should have, let me just make sure, yes, we should have the dedicated route set correctly here. All right. So let's see. Oh, right, GPIO stuff. So, all right, so there are no switches, so that goes away. right? There are no switches on this board. Yeah, that's right. Okay, and I can also delete the corresponding file for that. Let's see. There is no EEPROM I2C interface, but there are, well, all of the I2C pins, or all of the module control pins are separate. So I'm going to go ahead and copy all of those, right? Let's see. So those are all the pins. Let's see, where was I? I'll bring those down. Actually, you know what I'm going to do? I'm going to copy them from FPGA core because this has the complete set. Yeah, all of them. There we go. All right. Oh, and these are all int. Wait. I don't want those. That's why you always gotta double check yourself. Yeah. Don't need those pins. Okay, cool. So one of them is not present on the other board, and one of them was renamed. Okay, there we go. There are all the pins. All right, so now what we need to do is take a look at, well, let's see, hang on a second. This is, we're only interested in inputs, so we don't need reset. Hang on a second. Oh, we don't need reset in LP mode. That's fine. Okay. So this is QSFP. All right, so I'm going to go ahead and rename all these to QSFP0. And then these are all going to be QSFP1. Okay, excellent. And then that goes away. All right, so this is PCI user clock. Okay, so this is mod present. Okay. Okay. Let's see, what's going to be the simplest way to do this? I need to make two lists. Okay, so let's see. I'll just do all the stuff for QSFP1 first and then duplicate it for the other module. Let's see here. Okay, so all of the int pins. Actually, I do not need to add ints on all of the I2C pins. Okay, cool. So I'll go ahead and get rid of all those. All right. And the main one is this one. So this one, okay, I don't need O or T on any of these here. Right, it's just I. SCL and SDA, I. And then this one doesn't get int. And this one doesn't get I either. All right, because those are the inputs. All right, cool. So present plus those two. So for QSFP0 and for QSFP1. Then all that goes away. And let's stack this up a little bit anyway. I think I can put all of these. I don't want to put it all on one line, but I can do QSFP0 on one line and QSFP1 on another line. There we go. That looks good. All right. Let's go ahead and get this. Oops. There we go. Oops. Leave that. All right. So then QSFP. Oh. This should all be QSFP1. So there's 3 for QSFP1, and then the rest of this goes away. There we go. All right. So we have 6 pins that get passed through the synchronizer, right? Module present and 2 I2C input pins for each of the 2 QSFPs. That's not too bad. Okay, flash. That goes away for now. Oh, there's even more. All right. That will... Actually, on this one, that probably won't come back because I think on this one, you're supposed to access the flash by going through the BMC. So that's fine. Once I have the BMC interface, then that'll also be used for flash. All right, PCIe. I think I need to change the ref clock pin name. Hang on a second. I think this is just called, yeah, it's just PCIe ref clock P and PCIe ref clock N. So any reference to ref clock 1 goes away. Okay, very nice. I think everything else is good from that standpoint. Okay. Now I need to go ahead and swap out all of the phi stuff. Let's see here. I'm just going to pull that entire block from the Ethernet design here, because there's a few things that need to be changed, except I can remove these assigns. I think everything else is good. All right, cool. So I will come down now to, yeah, paste that in like so. All right. So that has all 4 channels, everything all laid out correctly. Except I now need to remove a couple of these signs here because these pins are being passed all the way through to the internal core logic, so they can be controlled over PCI Express. Okay, now let's see. I need to transfer over the GPIO connections here, the LED pins. That gets pasted in here, right? PCI Express, that's all good. Ethernet. All right. So for this, I'm going to go back here. I'm going to copy these pins. Right. So this goes, let's see. Perfect. So I tab that in. Okay, so that's int. Reset in, LP mode, those don't get int, and these are fine. All right, excellent. So I take that. Oh, these go away. Yes, okay, and then again, these go down here. And I'm gonna remove all of that, and I'm gonna remove all of that as well. All right. This is just feeding all of the correct signals through to the core logic. Now, one thing that we haven't done yet that you might have noticed is that these pin names are rather different from the top level pins here. Well, these are the same. These are 2 pins that go to the BMC, and then it's supposed to reflect the status of those on one of the lights. This one goes to the red-green LED next to that little expansion connector. And then these 3 control the other 8 LEDs on the back. Well, it's actually 16 because they're red-green LEDs, but those are controlled via a shift register. So what I'm going to do is write a bit of code that drives that shift register. So let's see here. That bit of code, well, let's see. I have a block here for those LEDs, and I'll go ahead and whack that down here. All right, so we've got the green and red inputs, and then merged here is just a way to combine these separate red and green signals into a single packed signal that we can use to drive the LEDs. So this is, I'm going to need to create this module. So I'll do that in a minute once I get everything else sorted out. So these are going to be running off of actually the PCIe user clock, right? Yeah. So I need to make a couple of small changes here, right? User clock and PCIe user reset. And this is going to be all double the prescale value. All right. Okay, let's go to FPGA core. Right. So let's go ahead and deal with all of these GPIO connections really quick here. So let's see. I'm going to go ahead and make a copy of all of these. just so I know what I'm dealing with. And now we're going to go down here to where all this stuff is defined. Okay, so we don't have a QSPI, so that goes away. We don't have EEPROM either. Well, most of the stuff is going to be changed. Okay, so modulo present, that's an input. Reset, LP mode, and, well, all of the, SDA and SCL, those are all outputs. Okay, cool. So reg. Okay, except this is a 1, and this is a 1, and this is a reset. Actually, I'm going to get rid of reset n. It's just going to be reset. Okay. We're not resetting it by default. Okay. And then that replaces all of that. Okay, cool. And then I'm going to take this. I'm going to duplicate this for QSFP 1. Okay. And then same kind of thing down here. Oh, right. All of this goes away, right? Yep. All that goes away. All right, cool. Okay. And get rid of reg. Well, this is reset n, right? So that gets set to the opposite of that. Okay. Get rid of that. All right. And then we have this duplicated for QSFP1. Okay. And now what I need to do is duplicate, well, not duplicate all these, but I need to put all of these down in the reset code at the bottom. So I go all the way down here, and no QSPI, no EEPROM, that basically replaces all of this. Okay, cool. So paste it in, tab it in, and all of these get replaced with non-blocking assigns. Okay, there we go. All right, so what do we need to do now? There's a couple of blocks that need to be updated to match with these newer register definitions. Well, okay, so one, the flash section goes away on both sides, right? Flash, yes, that goes away. All right, cool. And all right, so there's the GPIO I2C 0 and 1. So these are going to be connected to one of the QSFPs, right? So this is all going to be QSFP 0, and this is all going to be QSFP 1. Okay. And then this one here, QSFP 0 mod present n, QSFP 1 mod present, oops. Present, okay, there we go. QSFP 0. Oh, I don't have the interrupt pin connected, do I? Alright, that's fine. QSFP0 reset reg and QSFP1 reset reg. Is that it? That might be it. I think it's just those two pins. Yeah, reset LP mode, LP mode. Right. QSFP FP0 LP mode reg. Right. And I need to do that one more time. Let's see here. QSFP 1 LP mode reg. Okay. Now let me get the correct values for that. Again, this should come from here. These are some kind of standardized registers that I put together here. So present, fault, LOS. Okay, so LP mode is bit 2 in the high nibble. Okay, cool. Bit 2 in the high nibble would be bit 5 for this one here, right? That's right after reset. That makes things easier. And 13, there we go. Excellent. Okay, so this is reading the values, and then I need to write the values as well. Okay, so in this case, this is all QSFP 0. Okay, and then I don't have that one. And this is all QSFP1. All right, very cool. And then this one here, I have reset. Sorry, this is QSFP0 and QSFP1. And then I need to duplicate both of these here. LP mode reg, and that's 5. And oops. And this one here, this is QSFP1 LP mode reg is 13. Okay, so those are all the control bits connected. What else do I need to do? Oh, right, I need to figure out the board IDs. Let me take a quick look at my dev machine here. Oh boy. What should it be showing up as? 01. Oops. What did I do? Not sure what I did. I dragged and dropped something. Oh, I think I just reordered something. All right, cool. FPGA core. Yeah, all right. Excellent. Okay, so if it's not that, then I think it's showing up as like 80 something. Ah, there we go. Ethernet controller, Silicon Denmark device number 1. Okay. Let me take a look. If I look at that one, S810, that one, okay. Okay, 1C, 2C is their code, but I don't like just number 1. All right, well, I'll figure out a better code for that later, but this should be 1C, 2C. Right? 1C, 2C. Okay, cool. I'm gonna go ahead and transfer that to this one. Where were we? 1C, 2C, okay. And that puts it right above the Exablaze parts. So 1C, 2C, yeah, all right, cool. And then I need to figure that one out, so I'll start with that. Let's see, FPGA core. Let's make it 1, 2, 3, 4 for now. Okay, and I also need, oh, I got that already, didn't I? 4A 56093. All right. Is there anything else I need to do? Well, let's try running this through Vivado and see what happens. Oh, yeah, there's something else I need to do. All right, so 2 things. One, I deleted a file a while ago. Where was the corresponding make file? Did I not open that? I don't think I opened it, did I? Make file. Let me make clean real quick here. Okay. Okay. Let's get rid of that temporarily. All right, so this one needs to be updated as well to match the KU15P part. So this comes out of here, exit KU15P, that goes into the make file. Excellent. And for some reason that has a space at the end of it. Interesting. Okay. Kintex, okay. And let's see, I removed the debounce switch, but I need to add back the LED file here. All right. Let's see now. This is the LED SREG driver that I need to make. So we're gonna have fun making a new Verilog module here really quick. Okay. So this is going to be, I guess I still need that, don't I? Okay, so this is now module. Okay. LED SREG driver. Yeah, all right. And then I need end module. Okay, cool. So these are now all parameters here. Well, okay, there we go. Okay. Let's see. Well, I guess I need to check against this, don't I? Okay. That seems okay. Just so I'm getting things correct here. I'm going to put that down. Okay, LED SREG driver. That, okay, cool. Oh, I see, module. Right, the name goes here, doesn't it? Okay, cool. Let's see, so now I need to go through all of these guys. Okay. Oh. There we go. That's better. Okay, so these are all 1-bit. And then this is... Okay. That... oh, one more thing I need to do. How can I forget? Okay. Now let's get these aligned. And one more time here. Okay. So what is this module doing? This module is... Oh, let me save this real quick. This is LED SREG driver.v. Okay. Cool. So this module we're going to write. I'm going to be a little bit naughty and not bother writing a test bench for this. I'm just going to, you know, write the module. So what does this look like? What does it do? Well, what we want to do is take in, you know, a 16-bit vector that indicates the states of all 16 LEDs. And then whatever that changes, what we want to do is drive those states out into the shift registers. So on the FPGA board, there are two 8-bit shift registers that are connected end to end. So what we're going to do here is write a module to drive those shift registers. All right, so in order to do that, we need to make a state machine that can take in the LED signal and track when it changes, and when it changes, then shift stuff out to this shift register. The other thing to keep in mind is that the shift register chips are not very fast, so we need to divide down the 250 megahertz clock to something a little bit more reasonable. And we're going to generate this clock signal, you know, programmatically. So, all right, we need a couple of things here. So we're going to need a couple of variables. One of them is a count variable, basically, to keep track of the what bit we're currently outputting. And that's going to have to range up to at least one more than the count value, right? Because if we have 16 bits, well, we have to output 16 bits, and then we also have to give it a latch, basically, at the end in order to store the updated values in the shift register. Okay, so I'm going to create two local parameters here. So these enable us to create registers that can store both the count value and the prescale value. Let's see. All right, so here's the count register. Okay. Oops. Prescale reg. Okay, cool. All right. And then we also need, we're going to need a few other things, but for now, I'm just going to create registers for the outputs, actually. I'm going to, oh, hang on a second. It looks like the U250 design, well, the design's, the implementation run finished, but there's a critical warning. Go figures. Oh. That's odd. I'll have to look into that. Anyway, it looks like that completed. So we can test that out and see if it worked. I don't know why. This is one thing that annoys me about the way license files work, is that these cores have several features and they're licensed differently, basically. So depending on which license file you have installed, it might enable certain features with the design linking license. But for whatever reason, the tools check these in a bunch of places, but for whatever reason, they can't tell if you're using these features. So right now, it's like ANLT was enabled using a design linking license. Okay, that's nice, but I'm not even using that feature. So why are you giving me a warning? The feature shouldn't even be enabled in the core, I don't think. Interesting. I don't recall it giving me a critical warning for that before, but... Alright, whatever. I think that worked. Let me take another look at the other designs that we're running. Oh, that's the same one. Okay, this one finished. Let's see, this is the... Oh, okay, so with this one, it did close timing. 0.026 nanoseconds, positive, so that's good. We'll go ahead and test that in a little bit. It's using 100% of the GTs. You never see that on boards, but the reason is they locked out all of the other GT locations, so they're all used. All the ones that aren't locked out are all used. PCI Express, I'm using 1 out of 4. Well, that's kind of useless. You can't really use the other ones. Well, I guess you could like bifurcate 2x8 or something. I don't even know if the other ones are in an SLR where they are usable. Whatever. Okay, that seems fine. This one completed. I am not sure if it closed timing. I hope it did. Let's see if we scroll up far enough. This is the 10G design for the U250. This is too slow. Okay. Let's see, post-router timing. Yeah, okay, so that closed at 0.062. Not bad. Not bad, that looks pretty good. Okay. And then we have the U200. Same thing. Again, okay, so we get one critical warning. That's going to be from the same thing, complaining about the license. Let's see here. Update timing for bus skew, yada yada yada. Finalize. There we go. WNS 0.051 post router timing. So that closed timing. Okay. And last one. Let's see. So we got 3 out of 4 so far. This one finished. It generated a bit file. Now the question is, did it close timing? Let's see. Post commit optimization. Where are we? Oh, router initialization. Okay, I went up too far. Oh, there's generate bit. Okay, that's depositing routes. I guess it must have gotten lost in. Okay, there we go. Post router timing. There we go. Positive 0.03. So that looks good. 4 out of 4 closed timing. Now the question is, do they work? We'll have to take a look at that. Anyway, let's go ahead and write this one module first, and then we can take a look at bringing those things up and seeing if those designs actually work. Okay, so where was I? I need to make registers for the outputs here. Okay, so I'm going to go ahead. I'm going to make reg. Okay, there we go. And then let's assign these outputs here. Okay, so now what I'm going to do here is, depending on how things are wired, you might want to invert the output signals. Okay, so if it is inverted, then you invert the output, otherwise you don't. Simple. Okay, very cool. Now I need noise block. Let's see here. Okay. There we go. And in the reset block, we're basically going to reset everything that we need to reset. So in this case, we'll reset both of these, right? And we also need to reset all of these. Okay, very cool. So we'll go ahead and paste that in here, tab that in. Okay. Then we'll set all those to 0, and both of these need to be set to 0 as well. All right, very nice. Okay, so the next thing to do here is to generate a clock enable at basically the clock frequency that we want to talk to the shift registers at. Actually, it would be double that frequency. So we're running with a 250 megahertz clock. Let's see here. If we divide 250 megahertz by 64, you get about 3.9 megahertz. But that's going to be basically, you're going to generate a rising edge and then a falling edge, you know, one edge every 3.9 megahertz basically. So the result you're going to get is about half of that, which is about 2 megahertz or 1.95 megahertz. So, you know, that's within the range of what the shift register chips can handle. If you go too fast, then it's not going to be reliable. So this is where the prescale value comes from. Now the question is, what do we do with that? Well, what we're going to have to do is add another register, right? So we need reg enable reg. We're going to set that to 0. And then this also needs to be a reset. I guess not really, but let's see. Enable reg is set to 0. All right, cool. So now, in this case, we're going to set enable reg to 0 as well. I guess I'll go ahead and there we go. All right. And now to generate this clock enable, let's see. Actually, I'm going to call this prescale count reg, not prescale reg. Okay. So if the value in this register is non-zero, then we're going to decrement it. Okay, and that's all we do. Otherwise, once we hit 0, then we set enable reg, and we set the prescale count reg back to the specified prescale value. So the way this works is we drop, 63 in here, and then it counts down until it hits 0. Relatively straightforward. Actually, I probably don't need the +1 here, do I? No, because if we set this to 64, then you need 1 extra. Yeah, okay, so I think that's correct. Okay. All right, so the idea here is every 64, so with prescale set to 63, every 64 clock cycles, you'll get a single cycle pulse out of enable reg. Okay, so now what we do is we create another if statement here. So you might be wondering, why don't I just do all of this inside of this if statement? I'm going to put a bunch of stuff down here in a sec, but why don't I just do it inside of this if statement? Well, this if statement is looking at prescale count reg, which is CL prescale -1, or sorry, CL prescale bits wide. So if this is set to 64, then this is 6 bits. Okay, so this is taking 6 bits, checking to see if they, equal 0 or not. And if it's not equal to 0, then, you do what's down here. So everything in here is conditioned on these 6 bits. But if we set enable reg here, well, now everything down here is only conditioned on 1 bit. So it makes the logic simpler. It makes it easier for Vivado to meet timing. Okay, so what do we need to do down here? Well, there's a couple things. So the first thing, actually, before I start writing this, is that we need to synchronize the input, right? Because this LED thing, the idea is that this could be driven from really any internal clock domain. Okay, it doesn't have to be coming from the same clock domain. So as a result, what we should do first with the input signal is run it through a synchronizer that's a couple of flip-flops. Okay, so I'm going to do reg count -1 to 0. Okay, LED reg. All right, and now I'm going to make well, I'm going to make a copy of this here. Whoops, here we go. So I'm going to call this sync reg 1 and sync reg 2. All right, so I have a 2-flop synchronizer. Okay, so I do LED sync reg 1. I set this based off of LED, and then LED sync reg 2 is set based off of LED sync reg 1. Now I'm not going to set up any timing constraints right now. To do it properly, you would have to add, you know, async reg and max delay and whatnot. But for this little test, for the time being, I'm just going to leave it be, and if necessary, those can be added later. Right, so after we have these guys, now what we need to do is watch for changes. So the idea is we're not going to be sending out data to the shift register. We're not going to be sending out data to the shift register continuously. We're only going to send it to the shift register when something changes, right? So in this case, we're going to do LED sync reg 2 if it's not equal to LED reg. All right. And in this case, we're going to set LED reg based off of LED sync reg 2. And then we'll say it, then we need to indicate that we need to update. So I need to add this register. Okay. We need another register here that will tell it when to actually update. So the thing with this update register is I actually want to set update reg by default to be 1. So that means when the thing powers on, it's guaranteed to turn all the LEDs off instead of leaving them at whatever state they might have been in previously. So that's kind of important. Anyway, this is going to be, again, update reg. And 1 prime B, that'll be 1 prime B1. Okay, there we go. So, enable reg. Great. So if update reg, what are we going to do? Okay. Well, the first thing is we're going to clear it. So you can start to see how this logic is coming together, right? The LEDs will change. This will set update reg and store the value. And then we're going to hit this and we will clear update reg. Now, if this happens on the same site, then update on the same clock edge, then update reg will be left set at the end. This will override this if it happens at the same time. Okay, then we do count reg. We're going to set this to number 1 because we're on bit 1, right? So we're going to start, we need to count the number of bits. We start 1, 2, 3, 4, 5, 6, 7, 8. We go all the way up until we hit 16, and then we go back to 0, right? And then we're going to output this. Let's see here. sreg, dreg. We're going to set this to LED reg 0, right? So we're outputting 0. On the next cycle, we're going to output 1. Okay? That's pretty straightforward. Okay, so let's see. To output the rest of this, I now need to check to see if count reg is greater than 0 or not, right? If count reg is 0, then we're idle. If count reg is not 0, then we're not idle and we need to do something, right? So that's what this looks like, okay? So if count reg is 0, then we're idle and we'll accept an update. Otherwise, we have to output all the bits, okay? So in this case, we're going to do, well, how do we output a bit, right? What we're going to do count reg. Count reg plus 1, right? So we go to the next one, and then I'm going to do sreg dreg. We're going to output LED reg of count reg, right? We're going to output the next bit. So the first cycle through this, when update reg is true, we will set count reg to 1, and we will output LED reg 0. And then on the next clock cycle, well, count reg is now 1, so we will increment it, and it was 1 before, so we will output LED reg 1 into sreg dreg, and so on and so forth. Okay, that's pretty straightforward. All right, the other thing we need to do is we need to start pulsing the clock, right? So what we want to do is set clock high, then on the next enable, we want to set clock low, and basically do nothing else. Well, no, that's not what we want to do, actually. What we want to do is output this, right? We're going to update D, and then we're going to wait a cycle. On the next cycle, we're going to set the clock high. So that way you get plenty of setup time before that edge. Okay, so what we need for that is another register. Okay, so we're going to do, I'm just going to copy enable reg here. I'm going to call this cycle reg, because we're generating a clock cycle. Okay, so, and again, I need to set cycle reg. Do I need to set? Yes, I do need to set cycle reg to 0. And set cycle reg to 0. Okay, very good. Now cycle reg is 0. Now the question is, what do we do if cycle reg is not 0? Now this is going to basically override all of this. So all of this goes into the else block if cycle reg is not 0. Okay, let's see. Then I put, where did all those spaces come from? Else, there we go. All right, so if cycle reg, we're going to set cycle reg back to 0, right? And in this case, sreg clock reg, we're going to set this to 1. Okay, and now the thing is, in basically every other state, we want to set this back to 0. If that makes sense, right? Because no matter on, okay, so here's how it works. First time we go through this, everything is 0, so we end up here. We make sure clock reg is 0. If there's an update, then we set count to 1, we output the first bit, we're done. Next, enable pulse, we hit this, cycle reg is high, so we set cycle reg to low, we set the clock high, and then we're done. On the next enable pulse, we come in here, enable is low, count reg is 1, we want to set the clock back to 0, right? So that generates a clock cycle. And then we'll increment count and output the next bit. But now we need to handle the termination, right? Once we've outputted all the bits, we want to go back to idle. Okay, so what we're going to do is if count reg is less than count, right? If count reg is less than count, we do this. Okay. Otherwise, we want to set count reg to 0. Right. And let's see. What do we do in the last case? What we do in the last case is we need to set the latch. Okay, so in this case, we want to set sreg ld reg. Oops. And we basically want to do the same thing as the clock. Now in this case, we're not touching the cycle reg, but does mean that we want to clear this at other times. So we want to do something like that, right? Okay. Is there anything else that we need to do? Or is this basically oh, I forgot something. We need to actually set this cycle reg, don't we? Right? So in this case, we want to set cycle reg because we want to generate a clock cycle. And I also want to set that here because we want to generate a clock cycle. Here, we don't want to generate a clock cycle. We want to generate a latch cycle. I think it's LD. LD, you call it LE. There's a few things you could call it. Load, LD for load, LE for latch enable. You could call it latch clock or something. Yeah, so that's the idea. I think this is pretty much done. We should load it on the board and try it. Okay. Let me just make sure I haven't missed anything. Count reg is 0. We don't do anything else. Well, I don't need to touch, well, it's LD reg, I've already done that. Clock, I've already done that. D, it doesn't really matter. I guess we could set that back to 0, although that's not super important. I'll do that. sreg sreg dreg. Cool. Okay, so this will work. If we set this with 16 bits, then it will clock out those 16 bits, and then set latch high for 1 cycle to store those values, and then that's it. So there we go. Will it work? We'll have to try it on the FPGA and find out. Like I said, I'm not going to bother making a test bench for this because it's so simple. So we'll put it on there and we'll see what happens. Let's see. Oh, so now with this, I need to go ahead and add this to the make file, right? This needs to go up here somewhere. This is LED, what was it? sreg driver. There we go. All right. Excellent. LED sreg driver. Now there's one other thing that I need to do in FPGA core for this board is I need to go down to where the LEDs are set and configure them correctly. So let me go ahead and select all of these, because it's still probably pointed at the pins from the old device. Or not the old device, the alpha data board. Yes, okay, here we go. So I'm going to go ahead and put these guys down. This is going to be assign. I'm going to assign them all to 0, right? So let's see, put that in BMC. All right, so I'm going to split this one. Actually, not yet. BMC 0 and BMC 1. So one of the BMC outputs is going to be set to the PPS LED rig, and I'm also going to go ahead and put that on the expansion output, just so we're sure that it works. And I think, and those are inverted, so I'm going to invert them. I think these are not inverted. I also think they're not working at the moment because of a BMC firmware bug. But anyway, I'll go ahead and get rid of these like so. All right, and let me go back to fpga.v, and I'm going to add one more line from the Verilog Ethernet code. Let's see. I'm going to go ahead and add the one line that connects all of the block lock signals out to the LEDs. So that way we can make sure that things are actually working correctly and that the link is up. Okay. I think this is looking pretty good at this point. We might as well try running Vivado and see if it decides to cooperate. I don't know if it will. Moment of truth, right? Run make and see what happens. In the meantime, let's boot up my dev machine and we will test the designs for the U250, or U200 and U250, and see if they work. All right, so give me a sec, I'll get that thing turned on. All right, so now that my dev machines are up and running, let's go ahead and log in and see what things look like. Let's see. I'm gonna run dmessage over here. Oh, that's not so useful. I actually need to load the FPGAs first, don't I? Let's see, hardware, server, there we go. Okay then, so let's see, I'm going to start out with the 10G designs for both boards. Let's see, here's one, here's the other one. I will open up both of those. Actually, while those are opening, I'm also going to open up the implemented design here really quick for the 100D design, and we will make sure everything looks good in terms of the CMAC placement. Just to make sure nothing weird happened. I don't think anything weird happened, but it's Vivado. You never know. You gotta check. Okay. Let's see here. Oh. Why did we get a critical warning? Oops. That should be set property. Cool. I don't think that affected anything. Oops. I was a little overzealous with the deleting. Okay, that looks fine. I mean, it's complaining about the same thing, so it did close timing, yeah. All right, so that's probably fine. It was on a PCIe pin. Those should be constrained by the hard IP core settings anyway. In this case, the XDC files are a little bit redundant. All right. There we go. This is opened up on the U250, and I mean, let's see this connection. It looks kind of stupid, stretched out across the entire chip, but if it works, then it works, right? Main thing is to make sure that we're not crossing over. So let me go ahead and highlight leaf cells on this again. I'll do that one in a nice pink color. Interesting. And I'll do this one in a nice red color, or a nice green color, I think is what I did last time. Let's see. All right. So that's not too bad. Yeah, the main thing is I just want to make sure that this is going straight across to its associated transceivers, and they're not crisscrossing or coming from some far off corner of the chip. So, you know, not going to argue with that. Let's just make sure that there aren't any CMAC cores over here. This is Sysmon. This is, what was that one? Interlaken, that's right. And there's nothing here? Oh, that's the configuration. Yeah, I don't think there's any CMAX on this side. They're all X0, as I recall, and the transceivers in this case are X1, so yeah, go figure. All right, this is gonna work. That's perfect. And we can see that the PCIe stuff takes up just a huge amount of logic resources here. Just out of curiosity, let's see what this one looks like. This is the PCI Express hard IP core and associated logic. Boink. Yeah, that takes up the entire SLR for all of the transceivers. 16 lanes. That's a lot of transceiver sites. You know, four sites along there, along with all the associated logic. So yeah, that's quite a bit. And I think the ones that are peppered out through the rest of this are replicated reset regs. Let's see. There's 2 of them. That's interesting. Yep. 2 different reset reg replicas. Why would it put 2 of them immediately next to each other? I don't know. Anyway, that seems to be doing what it's supposed to. So, you know, that's pretty good. And no major timing issues, right? Setup. We met 0.026 nanoseconds, so perfect. All right. I'm going to set this one aside for the time being, and we're going to load both of these and see if things work. Let's see here. So the AU200, I'm going to open up the hardware manager here. Open target. I don't have it in the list. So I'm going to pick one on that machine. It's going to complain because it can't find the board. Whatever. I think it's this one. There's only 2 choices, right? And I picked the wrong one. Figures. That one. Yeah, let's close it. Okay, there we go. All right, looks good. Program device. And the make file puts the bit file in a weird spot, so Vivado doesn't find it until you tell it where it is. There we go, programming the device. Excellent. All right, so over here, we're gonna do the same thing. Open hardware manager, open target. Exact same thing is gonna happen. It's gonna complain bitterly. Assuming it connects. Okay, there we go. Yep, fair enough. And this one should now be the first one. Yeah, 250. Well, okay, there we go. Yes, that's what I want. Program device. And now I select the file. All right, so that one's good. I'm now going to go ahead and exit out of Vivado here. Yeah, close that. And just exit out of Vivado completely. I have compress bitstream turned on, but this still takes forever. I guess the U250 has a much larger FPGA on it. All right, that looks good. So I'll go ahead and quit out of Vivado. And now I need to reboot. Okay. Have to give that a minute. Guess I might as well check all of the XDC files to make sure I didn't propagate that error somehow. I don't think I did. I think that was just in a single file. That one looks fine. That was the U25010G, and the U250-100G wasn't complaining about that, so okay, cool. I guess it was just that one file. All right, that one's on the other computer. I'll put that one away for now. I don't think it's rebooted yet. I think needs a few more seconds. The kind of annoying thing about servers, they take ages sometimes just to boot up. These are not too bad, but some of the ones we have over in the CSC building, they take like seriously 10 minutes to boot. It's really annoying. And for some of them, they spend half that time in post. It's not even starting the operating system. Once it gets to the operating system, then it's done in like 30 seconds. But it takes ages to get to that point. These are super micro machines, so they're not too bad, but HP servers and Dell servers just have so much stuff that runs during post, basically. I don't really know what it all is. But anyway. Okay, there we are. That time it worked. Great, so I'm going to go ahead and pull up dmessage over here. All right, cool. So let me look at LSPCI. All right, so we have two instances here. The 01 device, trying to remember how the PCI Express buses in these guys are set up. So I think the 01 is going to be the U200 and the 81 is going to be the U250. Right, okay, let's see here. I'm going to go into the same thing here. Okay, and I'm going to go into modules. I'm going to build the kernel module now. Takes a couple of seconds. Okay. Now I load the module. Boom. Loaded one, I loaded two. Okay, there we go. That's good. All right, I'm not seeing any. Okay, so there's a couple of interesting things. The I2C bus appears to be working because it actually detected the multiplexers on there, and it's detecting one of the cables, right? And it's also detecting the EEPROM on the board. So that's on 8.1, which I can't remember which one is which. Whatever. Actually, we can tell now by looking at the board ID, right? Right. Okay. And then on the other device, we got the same thing. So this is actually detecting the EEPROM. So what we can do now, it's ethtool or ethtool-m, and then you give it the interface that you want. So this is now showing up as eth0, eth1. Oh, hey, there we go. That was able to read the EEPROM from the cable, and this one has a pure storage cable connected. I got a good deal on a whole stack of those. And then the other one, there we go. This is a fiber store cable. So these are both 100G DACs, or at least I think they're both 100G DACs. Yeah, so this one's either 40G or 100G. That's perfect. QSFP28. This one's also QSFP28. Transceiver type 100G. 100G based CR4. Not bad. or 25G base CR4. Okay. That works. So the I2C interface on both of these is working perfectly. That's great. Now the question is, does the Ethernet side work? In order to test that, well, I need to figure out what the other end of these cables is plugged into. It's hooked up to the same machine, but the problem is NICs seem to have two different standards with how to number ports. Question is, do they start with the port closest to the PCI Express edge connector or the port furthest from it? And I can never remember which is which. So I know that I plugged both of the cables into the same NIC, but I can't remember which port each one is in. So let's see. We'll test these one at a time. We'll start out with the U200, which is the one with the fiber store cable plugged into it. I can tell you that much. Okay, so that's E3. That's one of the NICs involved. Now let's find the other one. Let's see here. It's going to be one of the Mellanox NICs, and it's paired. So I think it's 193 S0 or F or S0 F0 or S0 F1. Oh, there you go. There's the fiber store cable on the other end. So this is where being able to read stuff out of the EPROMs is super useful, because you can read the cable serial number, right? And here we go. 18000-65582-1 and 18000-65582-2. So that's the same cable. We're seeing both ends of the same cable. That's perfect. Okay. Now, let's see. What I'm going to do is going to go into... I'm going to load a script that I have here called devnetns shell, and this is used for setting up network namespaces. I need to run this as root. Okay, so the great thing about this is it allows me to isolate the interface, so I can actually test the link without using two separate computers and actually force all the traffic to go over the link. This has previously been a huge annoyance. And I've had to like disconnect my computer from the Wi-Fi or whatever to force it to use a particular interface, especially if there's, you know, like network address conflicts and stuff between the board that I have directly connected and the network I'm connected to. I just want to send some traffic to this one board. Thank you very much. If you don't mind. So with this, you can make that happen. All right. So what I'm going to do is add an address. Let's see. So I'm going to add this address here. I'm going to put this on eth3. Oops. You'd run that as root. Okay. 10.0.1. Oh. Wait, do I need to do another thing? That says... Oh wait, that's up. Who am I kidding? Oh, I need to set this up though. All right, let's try that. Hey, there we go. Now I can ping, and I should be able to ping this way as well. Yep, that looks good. Now I'm going to do iperf 3 dash, let's see. I'll do dash S. Over here I'll do dash C 10.10.0.1. And we have a link. Yes, there we go. 9.4 gigabits per second. So that is 10G line rate. That design is working. Excellent. All right. Very cool. Now let's try the other link here. So we'll do that, and that was on What was it? ETH2? No, ETH1. There we go. All right, so we're going to do this whole thing again, except I'm going to set a different IP address here. I'll make this 11, ETH1. Same dang mistake as before. Okay, now I will set ETH1 up as well. And then over here, I'm going to go ahead and add, that was 10.11, right? Yes, it was. Excellent. So I will do that. And I can ping. And let's try iperf. Let's see here, iperf 3-S. Let's do a -C. Bang, it's connected, and I'm running it. Well, okay, there we go. Yeah, we're running at line rate. So hey, there you go. Both of the 10G designs work. Sweet. And it dropped 1 packet. Last time it dropped 0. I see. All right, well, that's a start. Great. The next step is to load the 100 gig designs and see if those work. So I already have this one open for the U250. So I'm going to go ahead and let's close the implemented design. Yes, go away. Yes, get rid of that. And I also need, that was the U250. I also need the U200 100G design. So same thing here. I'm going to go ahead and run Vivado from this guy. Okay, that'll take a moment to start. While that's going, I'm going to go ahead and open the hardware manager here. And let's see, go back to recent targets. Oh, I kind of need to be running the hardware server in order to connect to it. Wonder of wonders. Let's go ahead and start that. Oh, actually, before I do that, unload the module. That takes a moment. There we go. All right, cool. Okay, there's a hardware server running. Now I'm going to open the hardware manager. Yes, and let's see. Connect to same machine. Okay, let's try that again. Yeah, I know you're unhappy. Okay, this is the U200. I think that was the second entry here. Open target. Yes, there it is. Excellent. I will program the device. Bitstream file. All right, there we go. Program it. And this guy, same idea. We'll open that guy. All right, got to give it a second to think about it. It's trying to connect. Okay, there we go. No matching targets found. All right, whatever. I'm going to open this one. Open. Yes. And this one is programmed. All right, so I'll go ahead and close that. Yep, we're good. And actually, I'll just close this completely. Cool. Oh, wait, 3 critical warnings. Oh, I need to do that too. I see. So there's that one. Oy. Okay, so that's fixed now. And then I need to go to... All right, so this one, yeah, that needs to be commented out. And this one also needs to be commented out. Cool. Well, it still managed to close timing even with some of those duplicate constraints. So it was able to figure it out, presumably. Well, we'll see. Hopefully it works. But that should have all those problems fixed. So I'll go ahead and quit out of that. Did I program the device? I don't think I programmed the device here. Or did I? Whatever. Do it again. Not that big of a deal. In the meantime, what I'm going to do is reset both of those FPGA boards. Let's get out of that. Let's see. So this was 01, and then the other one was 81, right? Yeah. Okay, so that's one, and that is the other one. R14, no space. Well, this says bar 0 assigned, so that's fine. And that one also assigned bar 0. All right, I think it worked. If not, I'll reboot it. Okay, cool. So I'll close out of this then. All right, kill that. And now I will go ahead and insmod it again, and we'll make sure it loads both of them. Okay, there's 01 and the I2C devices and 81. Very nice. I think that worked perfectly. Yeah, I see the I2C devices on both of them, so that's perfect. And we can go ahead and confirm that we saw exactly the same thing. If I run ethtool, yeah, there's nothing plugged in. Bang, there's the fiber store, nothing plugged in, and there is the pure storage cable. Excellent. So we're going to run exactly the same things. Actually, I need to go into the correct directory again now. Verilog Ethernet. All right, let me go back up to that one. All right. So I think we added that address. All right, and I'm going to do the same thing here. This was E3. Set it up. E3, I need to add the address as well. Yes, all right. So I'll do ping 10.10.01. Well, it's not happy about that for some reason. Okay, well this is up at 100 gig. Right? Think so. Let's see if we're seeing anything via TCP dump. Nope. Okay. All right. Let's see. Sudo TCP dump -I F3. I need to add some -ns in here, I think, so I can actually see the IP addresses involved. All right, let's check the settings here. IP ADDR here, 10.10.01.24. Okay. Check that. We are looking at the FiberStore DAC. Oh, unless I have the ports mixed up. Is that possible? Doesn't seem likely, but I guess it's possible. Wait. The NICs may have initialized in the other order. Well, that would explain a lot. All right, let me remove that. And then I will add that to ETH1. Link set dev eth1 up. Now it works. Using the wrong dang NIC. Yeah. Alright, well hey, that just goes to show how useful the fact that you can query the cables now. That's, yeah, okay. Very nice. So that worked. Now let me check and see if iPerf works. iPerf 3-S. And why is it going slower? Let's try to run it in reverse and see what happens. All right, there we go. We're going faster than 10 gig. I need to have a better testing setup for this, I think. All right, let's try the other interface now and make sure the other design works. Let's see here. So what I want to do is add this one to E3. And I will set E3 up, and then I'm going to add the corresponding address here. Ping is good, and let's try iPerf. And iPerf also works. So hey, there you go. Both of the 10 gig and 100 gig designs for the Alveo U200 and U250 are working. So I'm going to check to make sure I don't need to clean up anything else. I'll commit those and we'll be good to go. Now we just need to wait on the Silicom design. Hopefully that doesn't take too much longer. All right, let me go ahead and clear out of all this stuff while we wait for Vivado. Okay, so Vivado has actually returned a couple of different errors. So let me go ahead and take a look and see if I can fix these. The first one is that this signal is named incorrectly. The correct name for that signal is PCI reset N. So I'm going to go ahead and take that, and this is going to be placed. You need to place it in 2 places so everything works correctly. Okay, that's issue number 1. What were the other issues? Oh, I missed a pin on the QSFP modules. Not sure how I did that. Anyway, there's this guy, interrupt N, right? So there's present, reset, LP mode, interrupt, SCL, SDA. All right. Yeah. Present, reset, LP mode, interrupt. This is also an input. All right, so that goes here. Oh, well, great. Okay. Okay, and then this goes right below LP mode, QSFP 1. All right, so that's there. And then I also need to go to FPGA core and add those same couple of signals. All right, LP mode goes after that. Tab that in a whole bunch. Okay, cool. And same thing here. Okay, great. So now this needs to be passed through and made available when you read. So that's going to be here. Now, what was the bit for that? Let's see. That's going to be in the driver MQNIC hardware. Let's see. Present in TX fault int n. So that's just the next bit. Okay, that's just bit 1. Okay. So I do interrupt n. Right, and then again here, this is going to be bit 9, and this is QSFP1, interrupt. Okay, there we go. That's good. Now, one other thing needs to be connected. Both of these signals need to be routed through the synchronizer here. No, where was it? Okay, here we go. Let's get rid of that. Okay. Int and one more. All right, very nice. So I go ahead and select that. and that goes here, and the QSFP1 version goes here, and then the internal ones go there, and one more. Okay, and that's adding 2 signals, so that goes to 8, right? 1, 2, 3, 4 times 2 is 8. Okay, and now I need to go down and connect them in one more place. So it's after LP mode. Oops, int. Okay, and one more. LP mode goes right here. Okay, there we go. Now I need to go ahead and restart Vivado. Come on, how long does it take Vivado to, okay, there we go. All right, there we go. So I'm gonna go ahead and restart it, and now it's going. So that will take a few minutes and we'll see if it works when it's done. Well, that failed out quickly because I had a typo. That should be 1. Let's see if that works then. Let's see. So this is what I got. Synthesis failed because, well, let's see. How far up do I need to go? Error. There we go. It has duplicate port connection for QSFP0 interrupt N. Oops. Let's run that again. In the meantime, I'm going to take a quick look at the 100 gig version and see if we can make that work. Or get it ready to work, as the case may be. All right, so we need, let's see, README, FPGA, need that, we need IP, mainly just these two, and make file, right? Okay, I think that's good. All right, let's see, so this one, well, this is still the ADM PCIe, so I need to go ahead and replace the file here with this guy. I'll copy that out and paste it in. Now all of this is the same. I need to comment out the reference clocks here, right? Otherwise it's going to get annoyed. I don't think I need to change anything else. I think everything else here should be correct. I'm running 2 different reference clocks. All right. Excellent. Everything else should be the same. Great. Now, let's see. I'm going to go to FPGA core, or actually FPGA first and then to FPGA core later. All right, so let's go ahead and copy over all of the clocking stuff, right? So we need to start out, well, clocking and GPIO connections. So I'll go ahead and take that. Actually, I'll just copy this entire block from FPGA.v here to FPGA.v here. Go ahead and paste that in, boink. Now, before I do anything else, let me make sure the PCI Express signals are correct, right? So there were 2 clocks, okay, and these both lose the 1, okay, and then there was the reset line, and that needs to be named correctly, otherwise nothing is going to work. There we go. All right. Nice. Is there anything else I need to do here? I don't think I need to touch the PCI Express code, but I need to do a number of other things. All right, so actually I guess the top level file should basically be identical in terms of the ports. So I'm going to go ahead and transfer that over. Like, while the stuff is fresh, just make the changes. Okay, so the clocking, I'm going to copy over the entire PLL, right? Clock and reset everything down to the bottom of the PLL gets transferred over because that's the same. Okay, excellent. Now GPIO, I'm going to transfer that over because that's not going to be any different. All the same connections, right? So that goes right until we touch the PCIe. All right, GPIO. Cool. Paste that in there. Okay, and then the other thing I need to do is I need to delete that file, right? And then I need to transfer over the LED driver code and place that alongside. LED sreg driver.v. All right, save that. Let's see. So that is good up to that point. We have the PCI Express changes. So now it comes down to the 100 gig CMAX. And I think these are going to be, are they going to be the same? I think they're going to be the same, yeah. Okay, so CMAC, right. USFP0 TX user clock 2, USFP1 TX user clock 2, all right, that works. CMAC pad, that's fine. So I think all of this is correct. I think mainly I just need to change the settings. So we have, there's the other Mac. Now here's the core logic again. That's fine. All right, so GPIO needs to be transferred. All right, there's the GPIO. Paste that in. I will, oops. I'll leave that one connected. All right, all the PCI Express stuff. Okay, so now for these guys, right. All right, so same idea. What am I looking at? FPGA.v here. I'm going to transfer over this block, right? Module present down through the I2C interface. Same idea. Module present, so I replace these two. Paste that there, and then same thing, I replace all of that, get rid of that comma, and then all of this becomes module 1. Okay, very good. Now for the core logic, FPGA core, excellent. So we need to make a similar set of changes here. So first we need the GPIO that gets transferred over. FPGA core, GPIO, okay, there we go. And then some changes need to be made down here. This one I need to be a little bit more careful with because the interface is rather different. All right, let's see here. So here's everything for the first module. I go down here and I'm basically going to replace the module pins there, and then same thing, all of this goes away and replaces that. Okay, now these all become QSFP1. All right, there we go. All right, and then I need to update these guys. I still don't know exactly what I want to use for the ID yet, so I will sort that out and update that later, but I will transfer the one that I picked for the time being. All right, that looks good. Now everything else should be good except when it comes to the GPIO registers again. So let's transfer that over. FPGA core, let's see here. Where were we? QSFP 0 and 1, the register definitions. So this goes ahead and replaces all of that. Okay. And FPGA core again, let's see. So I need to take all of the assigns, same idea. This replaces all of those assigns. Okay. All right, so now this gets down into the register definitions here. And again, a lot of this is going to go away. I might bring, well, I need to figure out how to do the BMC interface on this. That's going to be a problem for a different day. All right. Let's see here. We have the GPIO interface here. That goes ahead and replaces all of that, right? So we have the two I2C interfaces and the transceiver control pins. And let's see, let's go back to FPGA core again and grab those sections from here. Again, same thing, we're replacing all the flash and GPIO registers with that. All right, and I think, is this going to be the last change? No, I think there's a couple of other odds and ends that I need to do, but I'm getting very close. Let's see, I'll go ahead and swap that out. And the last one, I think, is the LEDs. Yeah, okay, so I'll just transfer that little bit over from FPGA core as well. I think that was down here. Yes, there we go. LEDs. Yep. Okay, very good. Paste that in there. Looks good. All right. Excellent. So let's go ahead. Oh, I need to update a bunch of other stuff too, don't I? All right, FPGA.xdc, I need to copy the part. And this is a 100G version here, right? So this is going to be, what was this? FB2CG at AU15P. And this is a Silicom, not alpha data. Okay, and replace the FPGA here, right? Save that. Let's see. So this one is good, this one's good, that one's good. Okay, those I need to work on. And then I will place this here as well. And this is going to be Kintex. Kintex U+. All right. And this gets swapped out with LED SREG driver. Excellent. All right, so now I'm going to go ahead and make clean. And all right, I need to edit a couple of other things really quick here. So CMAC US plus 0 and 1. I've got two of these. I think I'm just going to have to open up one of these in Vivado temporarily. Actually, here's what I can do. I'm going to go ahead and open up I'm going to open up the 10G design in Vivado real quick and figure out what settings should be, approximately. Again, we need to check the floor plan to make sure things line up correctly, because we have two of these sites, but this will at least indicate what the valid site names are. Oh. Something is not happy. What error do you have? Or is that cached from the previous run? All right, that could be an issue. Oh. I think I might need to edit the GT Wizard Ultra Scale for this. Yep. That's the problem. All right. One moment. I need to add a couple of lines to this. Let's see here. I thought I did. Maybe not. No, I guess that's hooked up to something else, isn't it? The plot thickens. I'm gonna have to look into that. But let's see if we can get the 100G design rolling for the time being. All right. So I have two of these that need to be updated. Let's see. So QSFP0 here is going to be on X0Y12. All right. So I'm going to go now into the IP catalog and let's take a look at the CMAC. There's two settings that we need to figure out for each one of these cores. Well, okay, so I guess the first one I already kind of know because this is 12 through 15. Yeah. So this is going to be, one moment. This is 12 through 15. 12, 13, 14, 15. Okay, cool. I mainly need to figure that out. Okay, and then for this one, this is going to be, it's the adjacent site skip 1, so it's 20 through 23. And this one went the other way, so 20, oops, 20, 21, 22, 23. Okay. So there should be 20 through 23. 20 through 23. Okay, excellent. So let me go ahead and select the same thing here. So for 0, we are on 12 through 15. 12. Oh, I need to select the correct. This needs to be CAUI 4. There we go. All right. Now that gives me some more options, right? So this is, oh, that's interesting. All right, let's try Y0. Nope. Oh, hang on. Is this the only option? Okay. 4 through 7, 8 through 11. No. All right, let's try 1. Okay, this is 20 through 23, right? No. Oh, this is 12 through 15. 12 through 15. Okay, so that is here. Let's see, 0. Does that list 12 through 15? No. 2. Does that list 12 through 15? It does. And 20 through 23. Okay, this lists 12 through 15 and 20 through 23. All right, so I'm going to try X0Y1. And then for this one, I'm going to try X0Y2. Presumably, that won't have a crossover. But there's only one way to find out, right? Yeah, okay. Let's see. I'll go ahead and cancel out of that. And I'll close Vivado here. And we'll go ahead and run Vivado for the 100G design and see how badly things fail. All right. Let's run that. And we'll see what that looks like. Let's see. Do a quick check just to make sure I didn't miss anything stupid, which happens quite often. All right, these look reasonable. I think we made all the necessary changes here. All right, we'll let Vivado do its thing and see what the result is. And hopefully, if it closes timing, then we can try it on the board and hopefully it'll work. If it doesn't close timing, then, well, I got some work to do. Okay, so it looks like Vivado finished. Let's see if it closed timing. All right, say anything so far? BitGen completed successfully. All right, so that's a good sign. And let's go up and take a look at what we got. Oh, well, that's not great. The design failed to meet the timing requirements. Please see the timing summary report for details on the timing violations. Well, let's see. How badly did that fail? If we go up a little bit further, we should see current timing summary WNS -1. Ooh, that's not good. And TNS -71. Yeah, that is really bad. All right. Let's see what happened. I'm going to go ahead and open up Vivado, and we will see what happened here. Hopefully it's something simple, but we'll see. All right, let's see. Let's go to 10 gig. We may need to make some sort of a modification here. All right. And we can also double check some of the stuff for the 100 gig design while we're at it. Oh, okay, that's interesting. So there's an error of some sort. Error, get property expects at least one object from TDMA BER channel TCL. And there's also a critical warning, and the critical warning is failed to meet the timing requirements. Interesting. All right. Well, let's take a look very quickly at this TCL script. So this TCL script is inserting timing constraints for this particular module that's called TDMA BER channel, right? Okay, so what the script does is it goes through the design and it finds every instance of this module, and then it goes through, it extracts the clock, the TX clock and RX clock, computes the periods of those, and then uses that information to attach a bunch of timing constraints. So most of this is either async reg or set max delay, or in one instance set bus skew. That's interesting. So what's happening is one of the get property, let's see, get property expects at least one object. So where is, there must be a get property in here somewhere. Oh yeah, here we go. Get property min period clock. Yeah. So this is, so what's failing is one of these commands where it's trying to read the clock period from one of these clocks. So what that means is that one of the registers that it found in the design apparently is not being clocked, which is totally wrong. So let's try and figure out why that happened. Okay, so let's open up the timing report. And to do this, we have to open up the implemented design, so this will take a moment. And I have an inkling of what it might be, because we copied all of this code from the Verilog Ethernet design. We may have missed a couple of the PHY connections, because this pulls out a couple of additional internal signals. So I may need to go through and add all of those signals back. Yay for copy and paste induced bugs. All right, so let me go into the original FPGA.v for this design that we copied, and let's take a look at how the PHY modules are instantiated. So here's this one, and here's that one. Yeah, we're missing a couple things here. Yep, we're missing all of these? No, we have block lock, we're missing the other ones. Yeah, okay. Let me find all of those signals. They gotta be defined around here somewhere. Ah, yeah, here we go. This has the PRBS31 enable and error counts in it. So I need this whole stack. All right, now Vivato's open. But I think we have figured out what the issue is. So I'm gonna go ahead and plug these in really quick. There's that. Those are all the connections. And all of these should be named correctly. So this should be connected. Yes, it is. Okay, cool. So now I need to go ahead and add or update all the PHY instances to match. So this is just all of, I guess, these 5 lines that needs to be added to each one of these. Well, I guess it's 3 added and 2 replaced to get the order correct. Yeah, all right. All right, this will take a moment, but at least that's relatively simple. All right, so this is channel 1, channel 1, channel 1, channel 1. And I replace those 2, right? Channel 2, channel 2, channel 2, channel 2. And again, these are all channel 3 now. Channel 3, 3, 3, 3. And this is now QSFP1, channel 0. I'm going to go ahead and copy that so I don't need to keep changing that. All right, 1, 1, 1, and 1. maybe I can do it this way. Yes, that works. 2 and 3. Okay, excellent. All right, let's take a look at the timing report and make sure we don't have any other issues. And we can also verify the placements for the 100G sites while we're in here. Let's do that first, actually, before I look at anything else. So this is one set of transceivers. What is this? This is, oh, that's an iBuff. Never mind. This is GTYE4 channel X0Y14. So that's one of the ones on this site, and we're looking at CMAC E4 X0Y1. And where's the CMAC core? The column is here. X0Y1. Oh, hey, all right. So that is exactly the correct one. And then if we go up to, this should be X0Y2 and X0Y23. X0Y2, X0Y23. Perfect. Okay, so these should be correct. We'll have to check to make sure that that closed timing when that finishes. All right, so let's take a look at exactly what failed. So here's the timing report. We got a negative slack minus 1.138 nanoseconds, total negative slack minus 71.655 nanoseconds. So what this means is that of all the paths that failed, the worst one failed by 1.138 nanoseconds. And then if you add up all 96 paths that failed, the total is about 71 nanoseconds. So yeah, that's not so good. Okay, but the interesting thing is none of the intra-clock paths failed. So usually with this particular design, the one you have to watch out for is the PCIe user clock. Right, PCIe user clock, and this is most of the logic runs in PCIe user clock. So this one actually met with plus 0.078 nanoseconds, which is pretty good. So it had no problem at all dealing with the core logic. What did fail is an interclock path. So this is a path from one clock domain to a different clock domain. And the thing is, whenever you see an interclock domain path fail, that usually means that the problem is with the timing constraints. Not 100% of the time, but most of the time, this will only fail if you screw up the timing constraints. So that's what happened. Well, that's roundabout what happened here. Basically, the timing constraints didn't get applied because some stuff wasn't connected that should have been. So yeah, that's not great. So let's see what this looks like. These are a subset of the failing paths, and let's zoom out. And we can take a look at exactly where these paths are. So, for example, here's one of the failed paths. Right. Hey, we're going from one register to another register. That is an incredibly short path, and somehow it failed. Well, it failed because the requirement is 0.8 nanoseconds, which is wrong. The requirement should be like 4 nanoseconds, I think. 4 or 6.4 or something, depending on what the clock periods are. So yeah, that's bad. I mean, the net delay going through here is, well, I'm not sure why the net delay is 2 nanoseconds. It's possible it had some hold issue or something that it had to work on to fix. Anyway, let's take a look at this. This is what a timing report looks like in Vivado. You can actually look at a schematic as well of what this looks like. We can view a schematic, although this is going to be an incredibly boring schematic. Yeah, if you have a timing failure between two rigs with no logic whatsoever, we're not talking about a propagation delay issue. We're talking about a timing constraints problem. So yeah, you don't expect to see this. Yeah, if you see this, then you have a different problem than something that you can fix in the RTL. So let's see what we got here. Source clock path. We start at clock RX clock out whatever on one of the, well, okay, that's what it's called. This is sourced from the GTYE4 channel. Bang, right there, RX clock out. So this starts at 19.2 nanoseconds relative to I don't know what, actually. Right, so it's a rising edge, and then there's a net with a delay. All right, so this is the fan out. Oh, the net fan out of 2 delay 0.086 nanoseconds. And then there's a buff G GT. This is the clock buffer, so that has a delay of 0.13 nanoseconds. And then there's the net for that huge fan out. You only see fan outs this big on clock buffers, or you should only see fan outs that big on clock buffers. Otherwise, this number is going to be really big. So that has a delay of 1.749 nanoseconds. So the total path delay is 21.165. Cool. Now the data path, we have a flip-flop, right? FDRE, this is phi RX error count reg 6, right? And then the destination, FDRE, is phi RX error count reg, or sync reg 6, right? Okay, so there's one net between the two that has an increment of 2 nanoseconds. That is huge. That is huge. There must have been it must have thought there was a hold issue that had to be fixed. So it added a whole bunch of trace to try and fix the hold issue, but then screwed up the setup time. So yeah, that's not great. But the thing is, these flip-flops are clocked by 2 different clocks. So the normal approach with timing constraints doesn't work because the timing between these two is not defined. You can't define it in terms of the clocks. Because this one here, this is coming from PCIe user clock, right? So this is saying this is 19.2, this is 20. But this is totally irrelevant because these clocks are asynchronous to each other. So this is incidentally also coming out of this is coming out of a GTH channel instead of a GTY channel. But that's the PCI Express clock. That goes through buff GGT and then eventually arrives at the flip-flop, right? So this is the clock arriving at the flip-flop. This is source flip-flop. This is the clock arriving at the destination flip-flop, and there's the destination flip-flop, and then there's the path. And then the last thing you do is you basically compare all of these numbers to figure out whether you're, ahead or behind. And this should have a number indicating what there's your slack. Where did they get that number from? Okay, here we go. Required time, 22.55, and the arrival time is 23.375. So it's the difference between these two. If this one is greater than this, you're hosed, basically. But the problem is this 20 and this 19.2 are just totally wrong, basically. Yeah. So this is, the problem is that the timing constraints. So yeah, let's rerun this. Hopefully with those connections added back, this will actually work correctly. And the timing constraints will apply, and this will close timing. This will probably work if I put it on the part, because the only things that are failing are these internal roots that are part of the bit error rate measurement stuff. So whatever, that's not important. I'm going to go ahead and close this and restart the run. And it looks like the 100G variant has finished. So I'm going to take a look at that and we'll see what that looks like. Okay, is this one done? All right, so that one, I'm going to kick this off as soon as Vivado exits. Let's see. Okay, there we go. Run make again. Excellent. And it failed again with the same error message because I forgot to go and add a couple of parameters. So, the parameter that we need to add, which was right in front of me before, but I totally missed, is to enable this PRBS31 subsystem. So I now need to go through and add that on every one of these PHYs. Cool thing is that takes like 30 seconds to do. So 1, 2, 3, 4, 5, 6, 7, 8. Great. Now let's see if Vivado is happy now. Starting Vivado again, and we'll see what happens. Okay, so it looks like the 100G design is done. I'm going to open it up in Vivado, and we will see what it looks like. Okay, there we go. Met timing plus 0.043 nanoseconds. That's pretty good. Let's take a quick look at the floor plan and make sure we don't have any weird crisscrossing with the CMAC cores. Probably going to be fine. From looking at the synthesized design, from looking at the Tenji design anyway, the sites looked okay, so we'll see. Okay, there we go. Now the design is open, so let's take a quick look at the CMAC cores here. So we'll take CMAC instance 0, we'll highlight leaf cells, have it a nice pink color, and CMAC 1, we'll do the same thing. How about this nice green color? Yeah, that's perfect. Yes, we can see the transceivers are here, and the CMAC is, well, in here somewhere. But they're nicely grouped together. They're not crisscrossing or something weird. So yeah, that looks perfect. That looks absolutely perfect. So we've got the PCI Express interface down here. We've got quite a bit of space. And then we've got all of the Ethernet interfaces up here. And there's still quite a bit of space around the outside for other stuff. So yeah, that's pretty good. And again, let's take a look to see how big this is here. If I highlight leaf cells, how about I make that yellow? Okay, yeah, okay. So that's quite large. This could probably be compressed down, you know, below this point or something if need be. But yeah, this looks pretty good. And at close timing, you know, no problem at all. And this one, was this in the core clock domain? Yeah, that was in the core clock domain. All right. Yeah, not too bad. That works. Oh, wait, no, this is something else. The PCIe user clock met plus 0.077. This is something internal to the PCI Express IP core. Interesting. Well, that looks good. Next step is to drop this on, on the host and try it out. Let's see. At this point, I'm still waiting on the 10G design, so I guess we'll test the 100G design first and see how it works. All right, so we'll open target. This is on the other machine. Well, it helps if I start the hardware server. All right, now that's running. So I'm going to go ahead and I'm actually going to add this to the list. Let's see. So that's, I think I want this one. Give it a moment. Yep, that's the card. All right, so we'll go ahead and do that. And it's running the default design, which apparently has a bunch of MIGs associated with the debug core. So go figure. All right, let's program this. Then I'll have to reboot the machine and we'll see if the card comes up as expected. I hope so. See if I closed all the windows from last time. Oh, this one is sitting on that machine. All right, cool. I think I did. All right, so that's programmed. So now I can quit out of that. All right. And we'll reboot. Okay, there we go. Now let's see here. So I'm going to go ahead and reconnect this guy so we can watch the logs. And over here, I'm going to go cd c. All right. Let's make sure the module is built. We'll go ahead and insert it. Okay, it did something. I see it registered an EEPROM, so that's good. Let's see here. And hey, there you go. We can talk to the module there, and we can see, yes, we have a QSFP28 installed, a fiber store cable, so that's perfect. All right, and then I'm pretty sure this is going to be hooked up to the Mellanox NIC, which I think is just, let's see, 193, I think, right? Yes. And this is a single port ConnectX-6, so. And there's the other end of the cable, right? 5569-1 and 5569-2. All right, well, that's very cool. So I'm going to go ahead and open up one more window. We're going to do exactly the same thing as before. And let's see here. All right, so sudo dev netns shell, and I want that. All right, let's see. IP addr add. So I will add it. And then let's see here. This was ETH0. Let's see if I can ping. And it works. All right, excellent. Let's see. Oops. I want to do iperf3-s, and this is going to be iperf3 as well. And it connects, and I run it 10 gigabits a second. Perfect. Now, if I run it in reverse, that should go a little bit faster. All right, very good. So the 100 gig design works on that card. So as soon as the 10 gig design is done, then we can go ahead and try that one out. Excellent. Now we're just waiting on Vivado again. Okay, so it looks like the 10G design is done. All right, Vivado is finished. So let's go up and take a look at what it looks like. Starting connectivity check. Where are we? Where are we? I want to see the end of place and route. There we go. I think this is right. Routing is done. All right. Post router timing. WNS plus 0.09. Perfect. So that one actually closed timing. So let's go ahead and open this up, and we'll load that onto the FPGA and see what it looks like. All right, there's Vivado. Oh, I need to start the hardware manager again. Let's see here. I will unload the driver first. Okay, and start the hardware server. All right. Oh, this one is now saying the WNS is plus 0.108. So that met very nicely. All right, let's take a look at the hardware manager. There's the card. Excellent. Whoa. Vivado just crashed. How often does that happen? Okay, let's see. There we go, met plus 0.108. Let's go ahead and open up the hardware manager and take a look, see if we can get this thing programmed. Okay, there we go, program device. And let's select the file. All right, there we go, it's programmed. So I'll go ahead and close the hardware manager. Okay, and I can quit out of that. Let's see. Let's see here. I am looking at 81. All right, cool. Scripts and PCI hot reset 81. Okay. Oops. Need to run that with sudo. Okay. And let's go ahead and load the module again. Okay. And let's go ahead and check on, let's see. Yep, we can still see that. All right. Now let's go ahead and add an IP address and set the link up and see if we can still ping the Mellanox NIC. Yep, there we go. Nice. All right, let's go ahead and try iPerf then and see if that works. And okay, there you go. We have it in the receive direction, and let's try the transmit direction. And there you go. We're running at line rate. Very nice. So there you go. We now have the Corundum design working perfectly on the Silicon board. So there you go. We ported Corundum to 6 different targets. Now I need to get this stuff committed and need to pick a final device ID for the Silicon device. But yeah, we're good to go. Okay, so it turns out that the LEDs on the card are not actually working. So that something didn't work. Let's take a look at Vivado and see if we can figure out what happened. First thing to look at in this case is to look at the implemented design and make sure the module is, actually there. So we'll open it up and take a look. Sometimes Vivado can optimize things away when it's not supposed to. Vivado occasionally optimizes away parts of the design if there's some issue with connections to modules and things like that. So we'll open this up here, see if we can find the module. If we can't, then I'll take a look at the log and see if we can figure out what happened. Okay, so there's the design, but I do not see the LED driver module in here at all. It should be at the top level, not inside of core, but it's not here. So that means Vivado must have optimized it away. So we'll go back to the synthesis log and see if we could find any warnings that might be related. So synthesis log, let's see, I'm looking for the LED driver. This is suspicious. Input port has an internal driver. Well, that's not supposed to be an input port, is it? That should be an output port. Oops. How many of you caught that? And have been screaming at the screen. When are you going to fix that? Well, alright. Let's run Vivado again and see what it says. Okay, so at this point, Vivado is finished, and, well, it didn't close timing, and there are exactly 8 failed endpoints. We have 8 LEDs. I wonder what failed. Let's take a quick look at that. But I'm thinking what we're going to have to do is actually properly constrain the synchronizers in the LED driver. So while this is opening up, I'm going to go ahead and create a new file for that. Now, with timing constraints, you can either create an XDC file or a TCL file. They're both essentially TCL scripts, but what you can do in an XDC file is more restricted than what you can do in a TCL file. So in a TCL file, you can have if statements and loops and things like that, which can make some things a lot easier. So I'm going to go ahead and save this as led.tcl. And we'll go ahead and make the timing constraints in here as soon as Vivado finishes opening things. Well, I'm going to take a look at an existing TCL timing constraints file as a reference. Let's see. So this is the one for the asynchronous FIFOs. Oh, Vivado has opened, and right, it failed timing. Cool, I know that. All right, let's see what failed. It's an interclock path. And it is, let's see, RX clock out 4 to PCIe user clock. Yep, every single one of those has exactly one failed path. If we click on that, what do we get? This is from the RX block lock reg to the LED sync reg 1 reg. Okay, there we go. That's exactly what happened. The requirement was set to 0.8 nanoseconds, and well, apparently added a huge amount of net delay to try and fix a hold violation, because since the clocks aren't related, the numbers that it's working with are complete junk. So yeah, okay, that's what we need to do. Now the important thing here is we need to know what the register names are. So Vivado tends to make some relatively predictable modifications to the register names. So in this case, the original register was called LED sync reg 1, and it was a part of a bit vector. So LED sync reg 1 in brackets 0. So what Vivado does, it adds underscore reg because it was a reg. So I do that in the code. I like to add underscore reg. So everything that shows up here basically has reg in it twice, which is kind of funny, but you know, that's just how it works. Anyway, so that is the signal in question. Well, actually, that's one of 8. But what we need to do is add 2 different timing constraints to all of these. Okay, so I'm going to start by copying this for loop into the led.tcl script. Let's see. Okay, so what this does is it iterates over every instance in the entire design. And well, actually it doesn't. It does get cells, and it's looking for instances with a specific name. Now, the reason we need ref name and orig ref name is because Vivado can actually create instances with different names. Now this is not like the instance name, this is like the original module name. And the reason it does that is when you have different sets of parameters specified. it will create an underscore parameterized some number version. So in this case, it's not particularly important because we only have one of these modules, but for other modules, it's super important. It's like for the FIFOs, for example, they're basically all going to be different parameterized versions. As soon as you change one parameter, it creates a module with a new ref name, but it keeps the original ref name, so you can search using that. Okay, so the next thing I need to do is, in this case, I don't really care about any of the clock periods. So when you're doing a clock domain crossing, what you need to do, well, there's kind of two main options. One of them is to set a false path constraint, where you're basically saying, I don't care about the timing of this path at all. It's completely irrelevant. In some cases, that's appropriate. In other cases, you actually want to constrain a specific delay, but you just want to ignore the clock paths, right? You don't care what the relationship between is between the clocks because it's undefined. They are asynchronous, but what you do want to do is make sure the path delay is relatively small. So for most cases, you're going to want to either set it to the destination clock period or to the smaller of the two clock periods. Either of those could be reasonable options. In this case, we're talking about LEDs here, so if we're off by a clock cycle or two, it really doesn't make any difference. So in this case, we're not going to try and set a specific path delay. I'm just going to set a false path. So for everything else, for example, for these FIFO timing constraints, well, actually, this does have some false path stuff, but the most important delays here are done with set max delay. So that's the idea. And data path only means we're going to ignore the clock paths on both sides. You have to do that in the asynchronous case because the clocks are not related to each other. Okay, so the other thing that we need to do is set this async reg constraint here. So I'm actually going to copy that little bit of code here, and then we'll rework it. Instead of reset flip-flops, I'm going to call it sync flip-flops. And for get cells, I'll keep the quiet, but then the rest of this will go away. And I'm looking for, so this needs to be set for both the two levels of the synchronizing registers, right? So we have LED sync reg 1 and LED sync reg 2, right? So we'll have the input coming into sync reg 1. This one is going to be set as a false path, and then sync reg 1 gets transferred into sync reg 2. So what we need to do is make sure these registers are placed adjacent to each other approximately, and that's what the async reg constraint is for. So what we need to do now is put in the names of both of these registers, right? So we're talking LED sync reg 1 reg, and then we have to say that that's part of a bit vector, so we name it like that. And then again for sync reg 2. Okay, so that will set async reg on these. And now the next thing we need to do is set, let's see, is actually set the false path constraint here. So this is get cells. I'm going to do basically the same thing, except we're only going to do this for reg 1. We're not going to do it for reg 2. These two are in the same clock domain, so you don't want to set a false path there. We just need to set it on the input of these. Okay. So the idea with this is going to go through all of the instances. It's going to pull out all of the cells that are called LED sreg driver. Then it will try to find any regs by these names. If it finds any, then it will mark them as asynchronous. and then it will add the false path constraints. And the reason that we need this is because even if you tie all of the LED inputs to 0, Vivado will optimize those away, so you won't have any of these signals. But Vivado will keep the overall module because it still runs one iteration to turn off all the LEDs when it comes out of reset. So you'll still have the module. This loop will still run at least one iteration. So we need to make sure we don't accidentally call set property or set false path with an empty list, because Vivado will complain about that. Okay, so now that we have this script, I now need to go add it to the make file. So I go down here and I add led.tcl. We save that, and now we're going to rerun Vivado and see what happens. And hopefully it'll close timing, and when we put it on the board, hopefully the LEDs will actually do what they're supposed to do. All right, so I'm going to hit generate bitstream, and now Vivado will run. So back in a minute. Well, a few minutes. Okay, so there we go. It looks like Vivado was able to meet timing. So let's go ahead and drop this on the FPGA and see if the LEDs work. Start up the hardware server. I need to connect to it. See if it is still in the list. Yep, there it is. All right, and then I will program the device. And take a look at it. And there you go, the LEDs are now working correctly. So there we go. We're done. We have all 6 designs operational, 10G and 100G on the Alveo U200, U250, and the Silicon board. So hopefully that's it for all of the porting that I'm going to need to do, or at least all the trivial porting. We're going to be looking at porting this to certain Intel devices, but that's going to be significantly more involved. And yeah, I'll have to see what's going to be in store for the next stream. So thanks for stopping by and listening in. Okay, so at this point, I'll take any questions that might have collected. I don't see anything in the chat, but somebody did post a question on Reddit, basically asking, why are we bothering to port Corundum to all these different FPGA boards? And I guess strictly, it's not necessary to do that necessarily, as long as it does what we need to do for the research at UCSD, and we just need to support whatever boards we're using. But in kind of the spirit of collaboration, we've worked on the core Corundum design for basically a couple of years now to get it to the point where it is now, where we're getting a reasonable level of performance. And I think that there's a lot of interest in the data center networking community to build on top of this reference design to experiment with new hardware features and whatnot. So we decided to make the design open source and put it out on GitHub. And to facilitate collaboration, we've decided to try to support as many kind of standard, widely available targets as possible. So anybody interested in using Corundum can simply download one of those designs and just drop it onto the board instead of spending, hours and hours trying to debug the design and get it to run on, the target they have in mind. And right now, most of the, all the Alveo cards have actually been donated by Xilinx. So otherwise, we probably wouldn't support those. And the idea is relatively simple. If we support all these cards, then it's going to make it a lot easier for other research groups to pick up Corundum and do something useful with it. So we'll see how it goes. I know that there are a couple of groups right now that are using Corundum for various things, but we'll have to see how it evolves. All right. Well, if there aren't any more questions, I will go ahead and sign off for today. For those of you who are still listening, thank you very much.